Ladies and gentlemen, on behalf of the organizers, I would like to welcome you to the International Conference on Material Science and Condensed Matter Physics 2024. Since the conference is a jubilee event, it's the 10th meeting in Chișinău, I would like to introduce you into a short history of our conference. Conferences. It was in 1990, a long time ago, that due to the fact that research activities and their results in the field of material science in the Republic of Moldova were already internationally recognized, thanks to the initiative of academician Sergiu Rădăuțan, Chișinău hosted the first really international scientific event, the International Conference on Ternary and Multinary Compounds, ICTMC. It was the 9th edition of this conference, and at that time Chișinău has the honor to host that prestigious meeting. More than 100 researchers from about all continents, and at least 200 from Moldova and all former Soviet Union participated in it. It seems reasonable to mention here that the ICTMC is a kind of wandering conference. The previous edition took place in France, and the next after Chișinău, the 10th one in Japan, Yokohama. And just two weeks ago, the 22 edition of the ICTMC were organized in Beijing, in China. This conference was a kind of trigger for us to try to organize a good conference in physics. In short, 34 years ago, many employees of the Institute of Applied Physics, and many people are here now, not very young, but anyway, of the Institute of Applied Physics actively participated in holding this conference. As a result, both the organizational and the scientific levels of that conference were highly appreciated. Shortly after that, in 1 year about, geopolitical changes shocked the former Soviet Union, and the Republic of Moldova, as you know, as all other ex-Soviet republics, became an independent state. After several years of adapting to the new changed environment, the researchers from the Institute of Applied Physics decided to launch a series of biannual conferences attractive for researchers working in such areas as solid-state physics, semiconductor material science, electrochemistry, photonics, and not only. As the first material science and condensed matter physics conference was held in Chișinău in 2001, and it was success of its organizers and participants, in spite of quite difficult financial situation. The next meetings, with a single exception, were organized biannually, and in 2018, 6 years ago, we had here the 9th edition of Material Science Condensed Matter Physics conferences, with the participation of about 270 scientists, among them about 130 people from over 20 countries. The 10th Jubilee Material Sciences Conference was envisaged to take place in 2020. However, because of the COVID pandemic and then the war in Ukraine, you had to change our plans. Today, we no longer have a pandemic, but unfortunately, that war still goes on. However, as in 2024, the Institute of Applied Physics marks the 60th anniversary of its foundation, it was decided to definitively have the 10th conference here this day in university. As you know, this 10th Material Science Condensed Matter Physics Conference is dedicated to the 60th anniversary of the Institute of Applied Physics. For some years, more than 50, it was one of the research units of the Academy of Sciences of Moldova. Then it worked under the Ministry of Education. And now it is in the framework of the Moldova State University. So, quite unstable. The Institute of Applied Physics was one of the biggest institutes in the Academy of Sciences. For some years, in the 20th century, there was an experimental plant within the Institute of Applied Physics. The plant was producing devices for processing of metal surfaces using electrical discharge machining technology. And the inventor of this technology and the initiator of opening the pilot experimental plant of the Institute of Applied Physics was the first director. It is just our conferences till to maybe 2016. And main areas of the Institute of Applied Physics, but now about the first director of Institute of Applied Physics, Boris Romanovich Lazarenko. They was also organized in the frame of the Institute of Applied Physics a specialized design and technology bureau of solid-state electronics for the development of electronic devices on the basis of work of the Institute of Applied Physics in the field of solid-state physics. Okay, something is wrong. Good. The story I told about the specialized design and technology bureau of solid-state electronics. Practically, this bureau was transformed into the Institute of Nanotechnology, the actual institute that works in the frame of Technical University of Moldova. Since 1970, the Institute of Applied Physics has been making publicity of its research and scientific cooperation through publishing the journal Electronic Processing of Materials, Электронная обработка материалов. Some articles from that journal are republished in the journal Surface Engineering and Applied Electrochemistry by Pleiades Publishing and distributed by Springer under the contract with editor-in-chief, academician Bologa, who was also the director, the second director of the Institute of Applied Physics in 1979-1997. Good. During 60 years of the existence of the Institute of Applied Physics, its directors were Boris Lazarenko, Mircea Bologa, Leonid Kulyuk, Alexei Simashkevich, Mihai Makovei, and now Olga Shikimak, whose photos you can see on the screen. More illustration on the life of the Institute of Applied Physics people during its 60 years, you can see on the poster placed just at the entrance of the whole Regina Maria, from the left side, it seems to me. It would just like to note that many famous researchers and founders of scientific schools worked in the Institute of Applied Physics. They are Boris Lazarenko, Yuri Petrov, Tadeusz Malinovsky, Sergio Radousan, Viktor Kovarsky, Dmitry Ditsu, Andrei Andriesh, Валерию Канцер, Всеволод, twin brother Всеволод Святослав Москаленко, Юлия Боярская, Александр Дикусар. Many more pages of the history of the Institute of Applied Physics you can find in the brochure by academician Mircea Bologă, which the registered participants have got together with the conference program and the book of abstract. Last but not least, my deepest gratitude goes to the organizing committee, program committee, international advisory committee, institutions, companies, and volunteers who have directly or indirectly contributed to the organization of this conference. We highly appreciate the decision of the European Cooperation in Science and Technology, COSTAction, SuperQuMap, to conduct the international workshop on emerging quantum materials based on superconductor nanostructures for the first time in the Republic of Moldova. Professor Fomin is the initiator. I hope we will have very informative, exciting, and encouraging discussions, exchange of knowledge, and establishment of new scientific cooperation. Thank you for your attention. And now I would like to give the floor to our VIP person, good Mistress Liliana Nicolaescu-Onofrei, Chairman of the Parliamentary Committee of Culture, Education, Research, Young, Sport, and the Media. Well done. Yeah. Yes, of course.
Dear Mr. Chairman Kutliuk, honorable members of the Academy, distinguished guests, distinguished hosts and participants, first of all, allow me to say that I will accept the nomination of VIP, but only for one reason, because I am an educationalist, and because I believe that people who work in education, these are the real VIPs. These are the people that change and can change the life of other people. Allow me to express my sincere gratitude for this invitation and the honor of speaking today at the official opening of the International Conference of Material Science and Condensed Matter Physics 2024. And on behalf of my colleagues from the Parliamentary Committee on Culture, Education, Research, Youth, Mass Media, and Sports, we would like to express our profound respect to all of you and to making this effort to all the honorable guests to come to Moldova specifically for the works of the conference. Indeed, we believe that the holding of the conference after several years is very important. It's important for continuous development of specific field of physics and materials engineering in Moldova, of course. I believe that it's also very important because of these opportunities to continue and to initiate new cooperation, new partnerships, and I hope that this will be results of partnerships between researchers and teams of researchers and team of the Institute of Applied Physics with our partners from EU and from all other countries present here today, represented here today. And there is no doubt that, of course, as I have been acquainted with the materials development for today's conference, I do believe that the conference is important for maintaining the image of the Republic of Moldova as a country that praises research and innovation, maintaining this image internationally. Secondly, at this anniversary hour, I would like to address all members of the Institute of Applied Physics and present our acknowledgements and gratitude for their work and achievements. Due to your enthusiasm, to your professionalism, to your work, probably we can say that the Institute has become such an important and quoted research center, not only nationally but internationally. Of course, it's important when you try to learn more about activities of such an institution. Of course, it's important to see all the data, all the statistics, all the rankings, all the quotations in the international research materials. But let me say, as a person that comes not from the real sciences, but from the humanities, I was very impressed with the quotation into the brochure developed by Mr. Bologa for the Institute, the brochure that talks about the Institute and the work for so many years. So let me just quote, because this for me, it's a part that should probably guide the work of many of us. And the quote says like that: "Unity of life and dream. In subsequent years, the strategic priority in research and innovation activities will be the European vector, the European and international integration. Responses to increasing demands include the preparation and presentation of projects, participation in national international programs. This anniversary is also an anniversary of 60 years of activity, an act of high responsibility, because the role and tasks of sciences in the new conditions are invariably increasing." I really am very proud to read something like that with the underlining of importance of our pathway to Europe and to European integration in a brochure talking about a scientific institute. And one more phrase, one more quotation: "Reciprocity and mutual understanding. This is the main thing. And of course, loyalty to the chosen path." I think that this phrase should be like a slogan for many politicians. Loyalty to the chosen path. This is true about scientists, but this should be true about politicians too. And this is true for my colleagues and those of us who tried to come into politics so that to change the way how politics are done in Moldova. And that's why I would like to thank you for this opportunity again. And I hope that you have ahead of you, all of you present today, but especially the Institute on this anniversary hour, I hope that you have a real path of continuing successes and looking forward to new projects and new conferences. Finally, I would like to present a modest award on behalf of my colleagues from the Parliament and specifically on Mr. Speaker Igor Grosu. I will do it in Romanian because I think Romanian has a lot of terms that are easily understood. Diplomă de gradul 1 se acordă colectivului Institutului de Fizică Aplicată al Universității de Stat din Moldova în semn de apreciere și recunoștință pentru implicare activă în realizarea proiectelor din domeniul cercetării și inovării din țară și străinătate, contribuție substanțială în susținerea și dezvoltarea colaborării științifice cu organizații internaționale, precum și cu prilejul aniversării a 60 de ani de la fondare. Cu deosebită considerație, Igor Grosu, președintele Parlamentului Republicii Moldova. Praising the work of all the directors of the Institute, Mr. Lazarenko, Mr. Bologa, Mr. Kuluk, Mr. Macovei, Mr. Shimashkevich, I would like to ask Madam Shekimaka to receive this diploma. Thank you.
Secretary of State of the Ministry of Education.
Yeah, thank you so much. Dear Chair of the Parliamentary Commission, dear academician Ion Tighineanu, dear Mr. Chair Leonid Kuliuk, dear colleagues, dear researchers, participants, honored audience. It's a great pleasure to welcome you all on behalf of the Ministry of Education and Research at the International Conference on Material Science and Condensed Matter Physics at its anniversary of 10 years and dedicated to the anniversary of 60 years from the foundation of the Institute of Applied Physics. Scientific research represents today more than ever the most important element of the development of a society for improving living standards, education, culture, and its general wealth of society. Strengthening the research and innovation system, increasing the contribution of the research and innovation system, and to develop the society and national economy, integration in the European area of research are priorities of the Ministry of Education and Research. We will stand on creating better conditions for our researchers, promote innovation and technological transfer, and attract young people to the area. The conference we participate today is extremely important from this point of view. Creating context to disseminate valuable results of the researchers from the Faculty of Physics and Engineering of the Moldova State University, Scientific Association Material Science and Engineering, Institute of Applied Physics of the Moldova State University, which are continuously conducting and publishing and benefit of constructing discussions among more than 200 participants of this conference from all over the world. Let me please use the opportunity to especially welcome the participants from Austria, Azerbaijan, Belgium, Bosnia and Herzegovina, Czechia, Croatia, Estonia, Finland, France, Germany, Greece, Israel, Lithuania, Great Britain, Morocco, Poland, Romania, Slovakia, Slovenia, Spain, USA, Turkey, Ukraine, Hungary, which made a long distance to be part of this important event. I wanted to mention each country and each participant in order to understand the power that we have here in this room today. I hope that the conference will create context for the establishment of new scientific cooperations, for the initiation of new joint projects within the framework of the European research and development programs and policies. Dear organizing committee, I would like to address you my gratitude for your effort in organizing this conference, for bringing through its participants Europe in our home country, and for maintaining the image of the Republic of Moldova internationally. And dear audience, today we are on the 1st of October, the day of foundation of the Moldova State University, a university that 78 years promotes the quality of education, research and innovation, which is continuously involved in societal activity and essentially contributes to the sustainable development of our country. Dear Moldova State University, my home university, congratulations. Great success to Moldova State University, great success to all of you in your research career. Thank you.
dear Chairman of the Parliamentary Commission, dear State Secretary, dear Chair of the Conference, good morning. First of all, I would like to welcome all the participants to this conference, and especially to welcome foreign guests, foreign participants, because in spite of instability in our region, in spite of instability in the weather, you are here and we can enjoy the conference. Academician Kolyuk told about the history of this conference, and I would like to know that we have a limited number of really international conferences. And I mean with the broad participation of researchers from other countries. And this conference is among them. And today we have already the 10th edition of the conference, which is really a success. And I would like I take this opportunity to congratulate the organizers for this success. And probably we should make reference to researchers that contributed to the organization of this series of conference. And it's unusual to see that in the room of the conference we have no well-known researchers. I remember our academicians, brothers, Sviatoslav and Vsevolod Moskalenko, who always where he participated, and many others. Probably today we should also make a reference to academician Valerio Cancer, who contributed much to the organization of this series of conferences, together with academician Leonid Kolyuk. Of course, we hope that in spite of difficulties, the research, scientific research will continue to be developed in the Republic of Moldova, especially taking into account that Moldova has been associated to the European framework programs. That means we can participate practically in all research programs of the European Commission. Besides, Moldova is doing its best to approach and to join the European Union. Therefore, we should keep the enthusiasm. I would like to know that research in this area always developed and development was based on the enthusiasm of researchers, because financial support always was very modest and now is very modest, but the enthusiasm of researchers actually allowed us to do good research, to publish good papers, and probably therefore many of you are here in this room today. I would like to note that this year the International Decade of Sciences for Sustainable Development starts, and in this connection we will have a number of events, and we will use them to advertise the research activities in the Republic of Moldova. I take this opportunity to thank Professor Vladimir Fomin, who is here in this room, because he played a major role in the organization of some events devoted to the International Year of Basic Research for Sustainable Development. And we will continue those activities under the auspices of the Academy of Sciences of Moldova. And I would like, on behalf of the Presidium of the Academy of Sciences of Moldova, to welcome you to to this conference to congratulate you with the opening of the conference and to wish all of you much success in your scientific activities. Now, it's really a very good situation that we have today the 10th edition of the International Conference on Material Science and Condensed Matter Physics, and at the same time we celebrate 60 years of the Institute of Applied Physics. And there was a decision of the Presidium of the Academy of Sciences of Moldova to give an award, Excellence in Research. Here it's written in Romanian. I will not read. Of course, it's underlined the contribution of the Institute of Applied Physics to the development of scientific research in the Republic of Moldova. And actually, the contribution, I think, can be appreciated at the international level, because the Institute of Applied Physics was and is still visible at the international level. Congratulations to all researchers from the Institute of Applied Physics. Congratulations to all those who continue with enthusiasm to develop scientific research in Moldova. And I would like to ask the director to come.
Conference, which after a break of 6 years, continue in this year our tradition of the international conference. And this year is a double celebration, as it was told, 10 celebration of the conference, 60 celebration of our institution. And I think that this conference, similar to the previous one, will keep this high level of presentation, I'm sure, and will give the possibility to establish new collaboration. We'll have fruitful discussions. And I think that despite the weather outside, will be compensated with the warm atmosphere of our conference, as became a tradition. So I would like once again to greet all the participants, all the guests, and welcome to Material Science and Condensed Matter Physics International Conference, and welcome to Chișinău, welcome to Moldova. Thank you very much.
And now, I would like to ask CHIFTINЫNU, the Vice Rector of the University. I would like to mention that the last 3 editions of our conference were organized together with the University of State in 2018 and 2016 as well. Please.
Dear State Secretary, dear colleagues, guests, and organizers. It's a great honor for Moldova State University to host and to organize a conference of an event of at scale like 10th conference, international conference in material science and condensed matter physics. I warmly greet you all this scientific conference dedicated to fulfillment of 60 years of excellence of Institute of Applied Physics and of State University of Moldova. I want to say a great thanks to Mr. Kuliuk because I will omit now part of my speech because he told about the history of Institute. I will omit this. It's not interesting to listen the same things twice. Just a short mention, but after a long history of changing founders, of creation of different independent centers, research centers, and their connection back to institute, junctions, and very dynamic development of institute, this organization finally became a part of Moldova State University, and our common founder is Ministry of Education and Research. Over the years, Institute of Applied Physics has trained a lot of notable personalities in various fields of physics. I will not repeat their names. I just want to say that, want to mention that most of them has very strong connections with Moldova State University. The Institute of Applied Physics has been over the years and remains in our days host of many important national and international projects in different fields of physics, especially in fields like nanotechnology, photonics, material science, and solid state physics. Now the institute have collaborations with National Aeronautics and Space Administration. This collaboration raises importance of institute research to a new qualitative level. Integration of research capabilities of the institute and Faculty of Physics and Engineering of university also contributes to this development by joint of use of human resources, tools and research spaces, selection of young researchers from ranks of faculties, licensed and master students. Integration into a digital infrastructure of State University offers to Institute of Applied Physics real opportunities to use joint resources, tools for research, security, access to and data exchange for international, bilateral and national projects. It's no coincidence that Oktoberfest is a double celebration. is the Day of State University of Moldova and day of the launch of the Jubilee Conference in Material Science and Condensed Matter Physics. The Institute of Applied Physics has become an organic component of the university, and the success of university education in the field of physics is now closely connected to the Institute. In this context, I invite you to use as efficiently as possible the opportunities offered by conference these days, which will certainly provide us with consistent, engaging and useful reports and presentations, stimulating discussions, project ideas, fruitful collaboration. Surely, this event will inspire and motivate the scientific community to continue exploration and discovery of new horizons in science. Thank you, and I wish you a fruitful conference.
Our event.
Dear guests, dear colleagues, I'd like to welcome everyone to this nice event, the 10th edition of the conference, International Conference on Material Science and Condensed Matter Physics. And before we start our scientific program and we go to the very first talk, I'd like to invite the conference secretary, Nikita Semenel, for a short announcement. So, Nikita, please.
Conference in today's conference program. The second talk of today's plenary session will be given by Dr. Marin Rusu. Just after the coffee break, the talk of Professor Shor will be delivered by Dr. Galina Gurieva. And at 12 o'clock, Professor Surit's flight was delayed by more than a day. So Dr. Evans from University of Warwick was very kind to change his time slot from tomorrow's plenary session to today's. And we also have a change of room. After the lunch, the topical session of growth and properties of advanced materials is moved from the room 241 to 530. It's the same building, just 5th floor. All the information is presented at the conference board. Please refer to it. Thank you.
Thank you, Nikita. Dear guests, all the updates on the conference program one can follow on the screens, on the TV screens next to the entrance to this Regina Maria Hall. So I'd like to invite for the first plenary talk of this conference, Professor Knapp, representing Warsaw Technical University and the Polish Academy of Sciences. Professor Knapp.
Good morning, ladies and gentlemen. Thank you very much for kind invitation. And I'm representing the Warsaw Technical University and Polish Academy of Sciences, where I came back after 40 years career in France, United States and Japan, and I started a few years ago to found a new Center for the Technical University of Warsaw and Institute of High Pressure Physics, Polish Academy of Sciences. As you see on the slide, there are a lot of words that may be difficult to understand for the public, but is mainly concentrated on semiconductor physics or material science. Do not be afraid. During my talk, I will explain you meaning of these words, and you will see that they are really related to the topic of the conference. My purpose is generally to tell you if and how graphene and gallium nitride plasmonic nanostructures can operate as terahertz voltage tunable photonic elements, detectors, filters, amplifiers, and sources. But before coming to the subject of the talk, the main discoveries and the research results, let me explain you a few basic words. So I organized my talk on 3 parts. First, I will tell you something about the terahertz science and technology, because it seems to me that it's something new, not very strongly developed in Moldova. Then I will try to tell you something about the terahertz plasmonics and how this plasmonics is related to nanotechnology, explain you why nowadays we can think about terahertz plasmonics and what is the relation of plasmonics with nanotechnology. And then I come to the last point about material science, how graphene and gallium nitride plasmonics can contribute to develop of terahertz science and technology. So, terahertz science and technology first. I have stolen this slide from my friend Taichi Otsuji from Japan, who prepares beautiful color pictures and a lot of information. I will stay for a few minutes on this slide. What you see on this slide, you see the electromagnetic radiation scale. From, on the left side, radio waves, then microwaves, then you see this terahertz gap that I will come back to, then infrared, UV, and X-rays. And you see the symbols of applications above all these regions. On the right side, you see imaging by X-rays that everybody knows, then visible radiation that is not only for sunburning, but for a lot of applications. Then you have infrared for the night vision or the guiding of small vehicles, if you like. And then on the left side, and this we are on the right side of the scale, these are photonics. Then you can have always the sources and detectors related with open gap semiconductors. Then the photon energy goes to smaller energies. We come to terahertz range that is on the border between the electronic on left side and photonics on right side. This range is often called the terahertz gap. Why? Because for a very long time, people had no semiconductors, sources and detectors for this range, and terahertz technology was not present and is still not very much present in our everyday life. Although this region is very useful for a lot of applications. What kind of applications? Terahertz waves propagate through air and through the fog and rain. So they can be used for the communication. They propagate on straight lines, so it can be secret communication. But they go also through plastic, through wood, through dry food. They can also be used for some diagnosis in medicine. Important thing about the terahertz waves is that terahertz waves concerns photons with very small energy. What does it mean? They are harmless for people. Contrary to X-rays used for imaging, the terahertz waves do not take electrons from atoms, so they are not dangerous for human. And what about the resolution in imaging? Well, the resolution can be in millimeter size because the wavelengths are in the millimeter scale. So this millimeter scale is very often good for imaging. All this domain of science that was born more than 25 years ago in the United States and Japan was summarized by many international committees, and leading countries was the United States and Japan. So I show you a very complicated Japanese picture with all these applications in it. Do not be afraid, I'm not going to go through this complicated picture, just to tell you that this is the result of the work of Terahertz Technology Trend Investigation Committee in Japan that started to work in year 2000, so 24 years ago. But I will show you a few examples out of the slide. First thing, this is the Metro card from Japan. This Metro card from Tokyo contains inside electronic circuits. You can check the quality of these electronic circuits by making the terahertz imaging. You see on the left side a visible photo, and on the right side terahertz, and you see all the electronics metallic parts inside, and you can check with whether this quality control. You make quality control to check the performance of this card and identify errors. We did similar things in Montpellier for many years. You see here the picture of ceramic knife. You have to check its quality. So you see on the left side the visible picture, on the right the terahertz, 0.3 terahertz image showing different density bands in this ceramic knife. And I was always making a joke that we are trying to take the taxpayer money, showing that this is a cutting-edge technology. So we did it for many years, and one of the important is agriculture and food industry. It's important for Moldavia, that is famous for vineyards, to check the watering of the vineyards, whether you do watering or you do not watering. And what you see here, you see 3 pictures of the leaves of vineyards. On the left side, at the beginning, you do not need watering, there is a lot of water in the leaves, but on the right side means, oh, there is no water, you have to switch on the watering of vineyards. So in the agriculture, terahertz imaging shows you how to use and how to make economy of water, not to make too much, and also to avoid useless watering. But most important application of terahertz is wireless communication, and this will be probably a breakthrough application. You see here this symbolic picture of different buildings or satellites. They communicate on straight lines, sending information. Why terahertz are important? They already exist in terahertz communication. This can be understood from the graph here that is taken from our French-Japanese communication grant. On the vertical scale, you have a carrier frequency of the carrier electromagnetic wave. On the vertical, you have the speed of the data transmission, and speed of the data transmission goes here logarithmic. You see 0.1, 1, 10, and 100 gigabits per second. And the goal of this fast terahertz communication is to transfer in the wireless way the data as fast as they come on the fibers. And on the fibers, they come in the speed of the 40 gigabits per second. And there is a very simple rule. If you want to transfer data with 40 gigabits per second without errors, you need the carrier frequency that is 10 times higher. And this 10 times higher brings you to the carrier frequency 400 gigahertz. You are already in terahertz range. And modern Japanese communication goes now at 300 gigahertz carrier frequency. Short-range communication, wireless, goes at 300 gigahertz. And this is the most probable, very nearest future application. Let me go. Oops, something happens. Maybe like this. Yeah. So I went through terahertz science and technology to give you familiar about the domain that I'm going to talk, and I'm working since many years. Now terahertz plasmonics and nanotechnology. This is the domain where I worked since a long time, and my purpose here will be tell you what is the relation with our plasmonic nanotechnology. This comes from this very simple picture and formula that I taken from Michel Diacono, that I had the honor to work with for many years in Montpellier. You see the bulk semiconductor here on the upper part of the slide. Here the plasma frequency depends on carrier density, effective mass, and dielectric properties. Here the frequency of this plasma oscillations does not depend on the size of the object. But if you take a two-dimensional gas with the gate like in the lower picture, the dispersion relation is completely different. You have here the letter K, that means the wave vector, and this wave vector is defined by the size of the object. And the second thing, you have this black part that is a gate at which you apply the voltage and you change the carrier density. So in two-dimensional gas with the gate, you get a full control of the plasma waves. You can change the carrier density, and also the size of the object changes the maximum frequency. And this is similar, to give you a little bit picture. As you see, the dispersion relation is that the wave vector is proportional to frequency. And this is the similar like in the sound waves. So to give you the nice physical picture, here I presented the analogy between the plasma waves and the sound. The frequency, maximum frequency when you get chief for the sound waves depends on the size of the object and of the speed of the sound waves. The speed of the sound waves is 300 meters per second, and the typical dimensions of the musical instrument is from 10 centimeters to 1 meter. If you divide two numbers, you will get the frequency that are in the acoustic range, 0.3 kilohertz to 3 kilohertz. What about the plasma waves in field effect transistors? You look on the right column, and what you see that the plasma field effect transistor had the dimensions 0.1 to 1 micron. And the speed of the plasma waves is 10 to 6 meters per second. If you divide these numbers, you get the frequencies between 1 terahertz and 10 terahertz. So, one important information, the plasma waves, like in the sound waves, that can reach terahertz frequencies, but only if the size of the object is in the micrometer and submicrometer range. So, now you understand that plasmonics, terahertz plasmonic, starts to be important now, because to get the real plasma oscillations in terahertz range, you need nanotechnology, you need objects smaller than 1 microns. And as I'm developing this analogy with sound waves, let me tell you that the plasma waves are better than the sound, because in the sound you change the frequency by the size of the object, but in the plasma waves you can also change the carrier density by changing the gate potential, like it is shown on this picture. This is, you see, the source, drain, and gate. This is the field effect transistor structure. And this, the frequency depends on the voltage, like on this formula, and on the size, that is size of the nanotransistor L here in the denominator. And you can, for gallium arsenide estimation, shows that this simple transistor can have a plasma waves that can change the frequency from 0 to 7 terahertz. So, two main important messages. Plasma waves in nanostructures can reach terahertz frequencies, and their frequency can be tuned by the gate potential. Therefore, the plasmonics is so important for terahertz technology. So, I promised you to tell how the plasmonic nanostructure can be used for detectors, filters, amplifiers, and sources. Of course, in this short 30-minute talk, I have no time to tell you all the details, so I show you only the main results about the detectors. This is our results from 2004, so this is the 20-year-old results on the silicon transistors. Silicon transistor, and you see here on the upper part of the slide, you see the typical picture of silicon transistor. Contacts, gate, drain, and source have dimensions 50 microns, right? But transistor is only 120 nanometer big. By capturing terahertz wave by the contacts, you can rectify this radiation and get this beautiful signal to noise ratio. Look, vertical axis here is on the logarithmic scale. There are many orders of magnitude between the signal and the noise floor. And it appeared that using these silicon transistors, we managed to get a room temperature record of the sensitivity for terahertz waves for 0.7 terahertz wave. And this was a breakthrough in this discovery that allowed people to make terahertz cameras and allowed us also to create two enterprises. One that produced this beautiful postal scanner, that you see the picture from the postal scanner on the left side. You see the envelope with the disk, and you have visible picture that is supposed to terahertz picture, and this terahertz picture shows that in this envelope somebody is sending your CD disk. And on the right-hand side, this is the French enterprise that we created 15 years ago, Terracalis, and what you see here, the guy who is technical director of Terracalis, who is keeping in a hand something that looks like the photo camera, but it's terahertz camera, handheld terahertz camera that is checking the quality of the glue of the windshield of the Renault cars. So terahertz detection is done already. Terahertz detection of plasma waves is done already. We are doing real applications. But what about the other applications? What about other plasmonic devices? I told you about detectors, filters. What about amplifiers and sources? Do we have anything about amplifiers and sources. Now we come to the graphene. And now you see this mysterious picture that I'm showing you from the beginning, on which you see the grating gate structure. This yellow part of the picture is the grating. These are grating fingers. On the left you see the source, drain, you see the current, and you see also terahertz wave coming and reflected from the structure. What was the structure? It was the graphene structures. And this is an experiment we did in Japan a few years ago. And what is suggesting this picture? That reflected wave has as higher amplitudes than incoming wave. That some part of energy was taken from current and through the plasmonic interaction given to the radiation. How was it done? What you see on this picture, that is a little bit complicated, but I will give you some keys. You see the plasmonic lines. This is the line that moves from the right to the left, this blue one. And this movement from left to right is because you are increasing and increasing current flowing from graphene. And what is seen here is that this frequency is going down, the amplitude is going down, and then from positive sign you change to negative sign for high current. What does it mean? That when absorption starts to be negative, you start to amplify. It is first demonstration of the terahertz wave amplification by grating gate structures. It was grating gate structure made of graphene. And on the right-hand side, you see the same evolution. You see the frequency going down, this blue line, and then kind of the gap, silence, and then the red part that shows you amplification. This is breakthrough results showing plasmonic terahertz amplification for graphene. And it was recently published by Physical Review X, very well-known journal. And what you see on this picture is this absorption, the blue valley, the changing to the red mountains, this is amplification. It was done in graphene. So you can ask yourself, why you're talking about everything is done? No, nothing is done. Because it was done on 20 micrometer graphene flakes. Completely useless. You cannot use it to any practical amplification. How was it done? The wavelength of terahertz is 1 millimeter. So how you can use the amplification on flakes? The radiation was guided to these flakes by needles. So this is demonstration of the effect, but everything is open. We have to make it to scale to bigger, you have to scale to bigger dimensions. So amplification of terahertz radiation by current-driven plasmon in graphene is impractical, no realistics, but effect exists. Flakes 20 microns are not practical. Terahertz beam is 1 millimeter size. So the question that we are trying to solve with the ERC Advanced Teraplasm project, can this phenomena be scaled to millimeter size systems? And here it comes the physics of materials. What kind of materials? Well, we try to see whether these graphene flakes can be replaced by gallium nitride. And this, now we come to the third part. Yeah, I see somebody is very astonished how zero gap semiconductor can be replaced by gallium nitride, which is wide band semiconductor, and why, right? Yeah, very, very nice. This is, I had a hard time to persuade the European Commissioner that it's really possible. Why? Because if you look for the gallium nitride field effect transistor, you can have as high carrier density like as in graphene. You can, at middle cryogenic temperatures at liquid nitrogen, you have a mobilities 10,000, 20,000 like graphene. So you can reach the same carrier density, the same carrier mobility like graphene. You can also get, you will see it, good terahertz frequencies by making nanostructures, and you can get a strong absorption. But contrary to graphene, you can get it on the big samples. Gallium nitride technology is technology existing on the few centimeters scales wafer. So you can really dream about terahertz devices made of gallium nitride, even in the first demonstration was in a graphene. And this I present my young collaborators, Pavlo Sai and Maxim Dub and Vadim Korotyev, who are the main authors of the results that I'm presenting now. that were working on grating gate gallium nitride plasmonic field effect transistors for terahertz optoelectronic devices. And this is the subject of this TerraPlasm ERC Advanced Grant that we have now to realize. We still have 4 years to show that gallium nitride can be as good as graphene. What is the challenge? As I told you, we need a few millimeter device, but you have learned from my lecture that to have terahertz oscillations, you need the objects of micrometer size. So how is it possible? You have to make thousands of micrometer cavities that covers millimeter surface. And it is a very hard task for nanotechnology. Therefore, plasmonics is 50 years old from first Chaplik papers, but practical realization can be done only now when you can make thousands of nanometer objects on millimeter scale. And this is what has been done by Pablo Say and Maxim Dub. You see, incoming terahertz beam comes to 2 millimeter samples, and with 2 millimeter samples, if you look, have stripes, metal stripes. They are submicron size. And this is a very hard nanotechnological side. You can do the small transistor, 1, even 1,000 transistors, but here you have to make stripes of 1 millimeter's length and 100 nanometers width. So this means like from Kishinev to Warsaw, but keep the distance constant between them of the few centimeters. So it's a really hard technical challenge. Only the best Japanese nanotechnology machine can do this. And we were happy to have it in Warsaw. So we managed to make 1,000 plasmonic cavities, and no even single was leaky. So this is a big technological achievement of my young colleagues from Warsaw, from Centera Lab. This is the main results. What is this on the axis? On the axis, on horizontal axis is the frequency. Sorry, you do not see the scale, but it starts from 0.5 terahertz and it goes to 3 terahertz. What are all these curves? These are the curves showing the terahertz absorption lines as a function of the gate voltage. Because I told you, when you make plasmonics, you can change plasmonic terahertz frequency by the gate voltage. We apply different gate voltage, and you see this plasmonic absorption moving from right to left, and all these pictures, let me speed up a little bit, shows these beautiful pictures showing on the right side a few harmonics, plasmonic harmonics, going to 0, and on the left side you have the so-called localized plasmon. I will not talk many about it. I will send you to reference of the Physical Review X that we published recently last year about this delocalized, localized plasmons that shows beautiful electrical tuning of plasmons. What is the conclusions out of this? You can make terahertz filters operating in good frequencies with gallium nitride, as good as graphene, even better because they can have a good size. So this is our PRX PRX publication 2023, electrical tuning of terahertz plasmonic crystal phases, and the main conclusion is that grating gate gallium nitride FETs behave as plasmonic crystals, not as single cavities. It works as a crystal. You need a crystal, plasmonic crystal theory. And grating gate plasmonic FETs may serve as electrically tunable terahertz filters. So next step, what is the next step? We have to follow this graphene way. We have to put the current. And this is the way that we are stopped now. We have a first preliminary experiments with the current, but we still cannot have a proof of the amplification, but still we have 4 years of project to do it. So this is the summary slide. Summary slide tells you in the pictures about the terahertz science and technology that can be applied for many, many things. Have a high application potential for quality control, safety, security, telecommunication, and this TerraPlasm ERC project has to show that the solid state GaN photonics can repeat in solid state something that is known as free electron lasers that works as a terahertz source but has a kilometer size and cost millions. But you can also think about the grating gates like small free electron lasers made in the gallium nitride, or maybe graphene, or maybe mercury telluride technology. And summary tells you that about terahertz science and technology, I hope I managed to persuade you that this important new science domain like spintronics or quantum technology, very actively developing. Number of the publications with terahertz in title rises every year. Then terahertz plasmonic and nanotechnology part that I was talking about tells you that you need nanotechnology, very high-level nanotechnology to reach terahertz region. So nanotechnology and terahertz are really related. And graphene and GaN plasmonics, I can tell you that passive nanodevices in flakes in graphene can be reproduced in large-scale gallium nitride. But there is an open question. Can one produce active terahertz devices, amplifiers and sources using gallium nitride technology? And this may be other materials that maybe will be one day produced here in Moldova, who knows? And this is a slide that tells thanks to my group in Centera Laboratory, and we believe that after this 50 years of research, terahertz plasma photonics can become a reality in Poland. Why? By joint forces acting in the same place and time. Why? We have a materials activity, materials synthesis activity, nanoscience processing, terahertz experiment, and the nice terahertz support that allows us to understand the two-dimensional plasmons. And I would like to make a special thanks to our group from Ukraine who is working with us, making calculations even under the bombs. Thank you very much for your kind attention, and I'm ready to take any questions. Thank you.
Thank you very much, Professor Knapp. The presentation is open for discussion. In the room you have our supposed assistants with the microphone. Please raise your hand and they will be next to you shortly. Thank you. Yes, yes. Hold on for the mic, okay?
High sensitivity detector. But of course, this is your hand. You are the source of the terahertz radiation. It's good enough to have a sensitive detector, and polymeter sees your temperature. So you have a black body. But existing sources are free electron lasers, or strong sources are also based on quantum cascade lasers, but they operate only at liquid nitrogen or below temperatures. You have also Schottky multipliers, very expensive, but efficient monochromatic sources. They are all devices that have no real practical use. You cannot put these devices to everyday use. And our efforts with plasmonics is to produce sources and amplifiers that can be based on semiconductor technology. This is the main challenge. So we have detectors, we have filters. Now we want to have amplifiers to amplify the signals. But on the silicon technology, on the semiconductor technology, that's the point. But there are existing sources, answering your questions, that are used by astronomers, by other people since many years. But they are difficult to use in the practical everyday life. Yes, of course. The power is the problem. Yeah, the power is the problem. They are very weak, and you have to use the cryogenic detectors to operate. And, well, by the way, my PhD thesis was on the terahertz. It was called in this time far-infrared physics. Now, far-infrared physics, and nobody wanted to take care and put any money on it. And then it was changed the name to terahertz, and now we can grab some money out of it. But this is exactly the same science we are doing.
Any other questions? Other questions, please?
Thanks for interesting lecture. You mentioned that between amplification and absorption you have a gap. What does it mean, this gap? That the terahertz are going through the sample?
Yeah, this is a very, thank you for the question. I show you. This is a very nice, terrific, I show you this graphene experiments. Yeah. You see here between the 40 millivolts and 80 millivolts applied to the sample is completely transparent. It's not amplifying. You have the same intensity incoming and outcoming. It works as a perfect mirror. No plasmonic absorption at all. And we do not really understand this experiment till the end.
This was my second question. Why? What happens there?
I have a kind of hypothesis. This experiment still was not repeated here in Europe since time, and reproducing the sample is extremely difficult. What we believe that when you're pushing, you have a kind of the two-dimensional gas cavities in the sample, many of these cavities. You push the current, at a certain moment of the current, you completely wash modulation, and you change from the independent two-dimensional cavities to the cavities that slow modulation that interact as a crystal. So you have this gap is between independent cavities, plasmonic cavities, and plasmonic crystals on the right. And I think plasmonic crystal is amplifying and independent cavities only absorption. This is the brief idea, but I cannot answer this question by clear physical arguments.
Thank you.
Thank you. I think we have to proceed to our next talk, but let's thank the speaker again.
Thank you.
So the next talk will be given by Professor Rusu from Helmholtz Center Berlin and Moldova State University. So the talk will be on electronic structure of surfaces and interfaces by Kelvin probe and photoelectron yield spectroscopy at ambient pressure.
So thank you, Sergio, for kind introduction. Good morning, everybody. So we will change it now a bit the topic. I will show you results of investigation by Kelvin probe and photoelectron yield spectroscopy, and what is striking here, conducted at ambient pressure. So because of this, so people especially coming from investigations in ultra-high vacuum, there is still some kind of skepticism. So my mission today is to convince you that this works, and I will present results of our investigations from the last few years. So I will introduce first briefly the Kelvin probe and photoelectron yield setups. I will speak about energy resolution and the information depth of these methods, and I will show examples of electronic properties of conventional and novel materials. So why studying surface electronics at ambient pressure? So first of all, because in ultra-high vacuum conditions, those aren't always suitable for investigation of easy volatile materials, and in particular of this self-assembled molecules on surfaces of perovskite materials, which are used in state-of-the-art solar cells. Secondly, is because we would like to develop facile methods which don't require high maintenance costs, and also for studying for high throughput characterization. So in this setup, so both of them, KP and POIS, one uses the same Kelvin tip, which is approached to the sample. The sample is fixed on this motorized stage, and the measurements are conducted in inert gas, either in nitrogen or argon, and the special measurements can be conducted also under oxygen or air ambient. So KP measurements are conducted in the dark, also under white light, and the different laser light, and also in this spectral range. PYS uses the spectral range between 3.4, 7.6 UV. And before I start presentation of results, I will show you what is the focus of our study. So electronic parameters is meant to obtain information about the work function of the materials and interfaces which define Fermi level position. And also, if flatband conditions are achieved under illumination, then we extend these values obtained for work function under illumination on the surface to the bulk properties. Next, so by considering this difference between measurements under light and the dark, we calculate the surface photovoltage, which indicates this potential barrier at surface, and also by the sign of SPV, so we can judge about which conductivity type material has, so in a non-contact method. Ionization energy is determined from PYS, so that also VBM position is defined, and yet, so if a band gap of material is known, then we can also define the CBM, find the CBM position, and in the end, so also electron affinity of material. So having a spectrum of PYS, from first derivative, we can subtract also density of state spectrum. Energy resolution of KP is between 1 and 3 milli electron volts, as here demonstrated on these gold films, and also on more complicated systems of these Kesterite films. For the PYS energy resolution is about 30 milli electron volts. Now about information depth. For information depth, by using this method, PYS, we get first into a small problem, because there are in this range between 5 to 10 electron volts, practically there are no available data, because all the calculations and also experimental data are presented for energies which are usually used in UPS and XPS measurements. So our first task was to find which information depths we have for our spectral range. So our approach is to compute inelastic mean-free path, because afterwards you can easily compute the information depths by multiply 3 times of information depth of inelastic mean-free path. And then we tune this universal equation, so-called, to fit all the data which are available experimentally or calculated for XPS range, and also to fit some few data which are either calculated or experimental to fit in this range. So here examples of calculated inelastic mean-free path, and in the end, so information depth, which can be appreciated from between 1 and 4 nanometers, yes, for this case, for materials comprising these elements. It could be also much higher for fullerenes. You have, for example, 6 nanometers for diamonds. It may exceed tens of nanometers. So this is how we measure the work function. This is a combined method where we measure the work function in the dark and then under illumination. So the ionization energy is subtracted from linear fits of photoelectron yield. And then we collect the data and calculate the VBM position relative to Fermi level. And if this is known, then it's only needed to know the effective mass of carriers, and then we can estimate with known effective masses, so the carrier concentration from our method. So this we are the first materials where we estimated this carrier concentration. It looks simple, but it's not trivial for application of this method. But you can see, so quite nice agreement between our data and obtaining ones from other methods. So here an example of estimating carrier concentrations on P-type nickel oxide thin films, which is a wide bandgap semiconductor, which is a hot topic for application in HTLs. And you need the characterization methods to understand, and it is a function of technology conditions, to make this material of not only of high transparency, but also of high conductivity. And here is an example shown how by oxygen plasma, by ozone plasma, these values of work function can be significantly increased, so that we bring these values of work function or Fermi level as close to VBM, or as way around VBM very close or on Fermi, so that in the end we demonstrate achievement of high conductivity, highly conductive thin films, and with those films, an example of application in solar cells based on this absorber of triple cation perovskite, we achieved 16% efficient cells. So you remember from these measurements I showed, it's about a nickel oxide ionization energy, which is about 5.3 electron volts. And here, so we investigate these core-shell structures with nickel oxide and zinc nanorods, and you can see this undetermined ionization energy, which nicely fits to the measurements we have conducted on thin films, on films coming from completely different groups and prepared by different technologies. So in the next, we measure also the properties of zinc oxide nanorods as substrates. We obtain the data necessary. We also have the work function data. And with those data, we plot the band diagram of this nickel oxide, zinc oxide nanorods. And this, in fact, is the first Venn diagram of this structure obtained on the basis of experimental data. And this helped our colleagues from Taltech to explain the effect or formation of these radicals of O2 minus and OH for degradation of the methylene blue in residual water. And when apply these nanostructures to these experiments, highest reported efficiencies of 70% were achieved. In the next, I show this our results on this combinatorial sample. So here we have a sample of new materials, which is abundant materials of barium copper selenide with a wedge or gradients in composition of copper and barium. So from here start with barium-rich side to the copper-rich side, and this is a sample of 12 by 50 millimeters. So in this way, so obtain a complete library. So instead of processing many thin films separately, all the information is here on this combinatorial sample. And now we investigate so the electronic properties, in particular work function is a dark and under the light, showing this mapping pictures. And we compute then SPV, which is positive for all the phases obtained, and showing that P-type conductivity of those phases from barium selenide to barium copper selenide and copper selenide. Then, because we have this quite good lateral or transversal homogeneity, then we decide for investigation of ionization energy to take line scans. And also you can observe how much the ionization energy changes from barium selenide to copper selenide films. Then we extract from these images line scans also for work function. We calculate again the VBM position relative to Fermi level, and this allows us to again to estimate the carrier concentration. It's a function of copper to barium ratio. So you can observe that for barium-rich material, we have a quite low carrier concentration. But when we go to copper-rich material side, so we obtain a carrier concentration which are a few orders of magnitude higher. So in fact, so here we demonstrate that for barium-copper selenide carriers can be fine-tuned by controlling this elemental composition. And the next here, we have an example of investigating of formation of interface between CIGS absorber and cadmium sulfide interface. So here's as a function of deposition time of CBD cadmium sulfide. So here we have values of work function on the bare surface of the CIGS, and you can see these stars, they indicate the reference data. Also, for cadmium sulfide, we have a very good agreement. And the development of work function and also of ionization energy with the deposition time, it also follows and correlates very well to this CDS growth stages, which includes an etching stage. So it is not surprising that after the first minute of cadmium sulfide deposition or immersion in CBD bus, you don't find any cadmium sulfide yet, but the surface is etched. Therefore, so here when obtaining and the VBM and CBM development as function of cadmium sulfide deposition time, we will not consider in further in plotting the final diagram of this indium selenide phase because it is etched. But of course we will preserve this indicating on the electronics of the bare surface. Considering also the properties of the bulk thin film, we plot the entire band diagram, which was used afterwards for simulations, and we could demonstrate on this device achievable efficiencies of about 18%. On complete devices, we investigate the band diagrams in so-called layer-by-layer investigation. So here we have electronic parameters obtained for any of layers in this device structure. So again, you can use all this data for simulations. So one interesting point here is, oops. Okay. Sorry. The interesting point here is that this recorded work function for silver, which is much lower than the measured on the references or on a SiC silver film with a work function of 4.7. The point is, this is a work function of 7 nanometers of silver, and this we supposed that it formed a mixed film of silver and BCP. So this was confirmed then by other complementary measurements. So investigating the band diagram and in conjunction with the development of SPV in layer-by-layer investigation, we can conclude about development of VOC of device or development of built-in potential in the device. And this is completely different from conventional devices, because here we observe that its built-in potential formation is very much dependent on work functions of applied HTL and ETL films. In the next, we demonstrate manipulation of the electron affinity of electronics of films by applying sums. So in one case, applying this flat molecules, we can shift downwards the local vacuum level, producing this negative dipole. Another type of molecules is used, by contrary, to shift the local vacuum level upwards, so obtaining a positive dipole. And in our work function and KP measurements, we demonstrate the changes on the surface, electronic surface, is really by producing this surface dipole. So this means in case of changes of both work function ionization energy or VBM, we have to expect changes in values by the same energy. And this is the case, so we demonstrate by KP APS measurements. In the next, here we demonstrate also manipulation of surface electronics of diamond, but in this case not by molecules, but by atoms of oxygen and hydrogen. And the effect on 100 cubic diamond is so strong when applying hydrogen surface termination, then we can achieve negative electron affinity. So meaning you have the vacuum level below the CBM. So we investigate single crystals terminated by hydrogen and oxygen as references, because for applications this would be too expensive, but we investigate thin films of this boron doped black diamond, also terminated by hydrogen and oxygen. And the applications or target of experiment is for application in cold emitters. So we demonstrate this high values of negative electron affinity of single crystals, and also same this tendency and behavior of electron affinity is observed for thin films. But you can see that amplitude is much lower, and probably this is related to or having some defects in these films. Then from density of states spectra, it was here on this new material when we have observed this nice, I would say, agreement again between this DFT calculated spectra and our experimental spectra, which are shown here with red. So next, we have again observed quite good density of states spectra, I mean, which we could put in correspondence as a function of cadmium to zinc ratio. So we can see that also integral changes, but also amplitude. And we can see also that this spectra agree well with the calculated ones by different groups. So here in between copper zinc tin sulfide and copper cadmium sulfide. Also in other experiments on this perovskite films of cesium tin iodine and also of cesium tin lead iodine, on these combinatorial samples, you can see that quite defined density of state spectrum can be attributed to a certain composition of the film. So for us, again, it's interesting to find the effective mass of carriers, but not always, so you can find it in a calculated or experimental one. And our goal here is to extract the density of states and then effective mass from this spectra. You need good reference samples. We work on this, but at the moment we can demonstrate that by having at least one point on the sample with known effective mass for certain composition, in this case, so it's 1:1 lead to tin, so then we can compute the effective masses for other compositions by considering the integrals of different compositions compared to the reference sample. So again, we use this obtained data. We consider different statistics for semiconductor on non-degenerate and degenerate semiconductor. We obtain this data and we compare with data obtained from other methods, and we can see quite nice agreement. So in summary, we have demonstrated good agreement between measured work functions and ionization energies on series of materials, so with the published data. We demonstrated applicability of KPPYS for determination of material charge current concentration. I demonstrated mappings of combinatorials in films for high throughput characterization of materials. We show applicability of the combined KPPYS for detection of surface dipoles induced by both suns and atoms. So we show detection of negative electron affinity of 100 cubic diamond, surface as dependent on surface termination, and we show good agreement between measured and calculated total dose spectra and calculation of effective masses of holes against the reference sample. So these are our acknowledgements, and I thank you very much for your attention.
Thank you very much, Professor Russo, for this nice and interesting talk. And the presentation is open for discussion. Please raise your hands, and you're going to get the microphone next to you. Questions, please.
So I hope I was convincing with these results, and if there is points for collaboration, so please let's discuss and send your samples for characterization. Yeah? But also please ask questions.
Yes, one question here is whether your method is show some surface properties like surface states or special effects of the electronic structure on the surface.
Can you repeat a little bit?
Whether the measurement is sensitive enough to show electronic properties of the surface, like surface states or...
Yes, so in fact, these are surface sensitive methods, and really so, because I demonstrated, so how do we influence electronics by terminating surfaces, or so example with oxygen and hydrogen. So it's in fact demonstrated that method is sensitive for detection. Of course, one has to pay attention to information depths, because sometimes you can obtain, as a function of information depth, information not only from very surface, but also from the states, from bulk. So we have to distinguish them. And yeah, so probably if you paid attention for negative surface dipoles, so when one had these flat molecules where we speak about sub-nanometer thickness, yeah? Then there we had a small difference between measured work function and ionization energy. So it would be one of the indication, like it's a difference between very surface sensitive KP, Kelvin probe, because you don't speak about information depth in this case. It's a very sensitive surface. But for ionization energy, you still have. So that you, when you take the difference between work function and ionization energy, so you can see this difference.
Thank you. Any more questions? Yes, please.
Do you have to clean the surface in a certain way before performing the measurements?
in these experiments and all the samples we measure, they are transferred from not breaking, not bringing the samples in air. So this means we transfer samples from one glove box to another glove box. Samples are fixed on measurement stage, transferred again to setup, and without exposure to air. Yes, but of course, so as in the case of XPS, we could also clean surface, and also in experiments in layer by layer cleaning, moving samples, checking how the electronic changes, and also like in XPS measurements, when you achieve a certain point, certain, like you don't see anymore the changes in the electronic properties of the surface, so you think, okay, before that we had some oxides, or you had some surface dipoles, some collected carbon or water molecules from air, but starting from there, so you have already bulk conditions.
Thank you. Any other questions? I have a short one. Can you comment, Marine, some things on limitations of the method you use?
Is any method, so it has limitations of application. If speaking about PYS, of course I would like to extend characterization in more deeper in UV, so exceeding, for instance, 7.6 UV. Of course, then you need special lamps. You have you need special detectors for calibration of the spectra. But we work also in this direction. If speaking about Kelvin probe, then at the moment, so we have a limitation of time resolution of about 100 milliseconds. And I would prefer, of course, to have a resolution to go in nanoseconds range. So, and then I could then find from CPD decay or work function decay, well, CPD decay, also carrier lifetime.
Thank you very much. Okay, any questions? No? Let us thank the speaker again. Thank you. And before we move to the next presentation, just as it will come to an end, I'm going to come to a few more announcements for the conference attendees. So please stay tuned for the announcement. Thank you. The next talk will be given by Valentin Crăciun from the National Institute of Lasers, Plasma and Radiation Physics, Romania. So the talk will be on pulsed laser deposition thin films for advanced applications.
Thank you very much, Mr. Chairman, for the nice presentation. And also, I'd like to thank the organizer for inviting me here to share with you our results. My mother was born in Moldova, so whenever I hear Romanian speaking around me, I feel at home here. and sounds what I was hearing when I was a little boy. So I'm going to talk about pulse laser deposition of thin films for advanced application. Here are the authors from our group performing this research, and also the acknowledgement for the funds. Here is the outline. First, I will talk about pulse laser deposition of high entropy alloys thin films. Then I will present some results about our new method for measuring laser-induced damage threshold, especially for femtosecond laser, using oxide films grown by PLD. Again, for femtosecond laser, I will present our results about carbon foam, and I will end with some conclusions. High entropy alloys were discovered more than 200 years ago, but for quite a very long period of time, till the turn of the century, they were not used in application. And then people realized that they have very important application. Probably they haven't used it before because at that time the statistical thermodynamics was not well known, but it disappeared, the pointer. Okay. But the entropy of mixing is so high in these materials that they are very stable in terms of phases, and there are very low possibilities for secondary intermetallic physics to appear. And also when you mix things together, you end up with a very defective lattice. And this distorted lattice, thank you. This distorted lattice with one and here many elements give new properties of stability, sluggish diffusion, new properties to the cocktail effect, and so forth. These materials were prepared in Bucharest. Professor Janta has a nice setup. Basically on a copper plate that is water cooled, there are placed the materials that you want to synthesize. So here are the mixture. Then you perform the electrical discharge. You flip the samples over several times in order to obtain a good homogeneity. And then you look at the microstructure, and we see some dendritic matrix, grain boundaries, and some intermetallic compounds if we didn't do quite a perfect job. But here is an image of ion K-line, a map, to see how homogeneous the material is, and as you can appreciate, it's rather homogeneous. Our first investigation started with a bulk alloy series of aluminum, cobalt, chromium, iron, nickel, and nickel had various concentrations starting from 0.2 to 2.0. When we perform X-ray diffraction of this series of materials, we've noticed that we start with a pure phase BCC, and then for a certain nickel concentration, as it keeps growing, we reach a mixed phase. And continuing, we end up with a pure FCC phase because nickel tends to, for high concentration of nickel tends to impose his structure on the materials. So from this series, we choose 2, 6, and 10 with various nickel concentration. And here are the structure of the targets. We see we started with, we had a pure BCC, a mixed phase, and pure FCC phase. Here is about the efficiency of production. That's the element that were used to be melted together for these targets, and the efficiency is pretty high. This is an SEM, these are SEM images for films grown using pulse laser deposition. We have used a krypton floor laser with rather high fluencies, 40 Hertz, and we've made deposition either in vacuum of the order of 10⁻⁷, millibar or in nitrogen to try to induce. This is a typical image of surfaces when you use PLD. It's a splashing effect and we end up with a lot of droplets, but still the film right here in between the droplets, it's very uniform and dense. Here are the electrical measurements. The resistivity, which was calculated from the 4-point measurements, and the thickness of the film estimated by ACM on cross-section. These values are typical for these high entropy alloys. They are much higher than your typical metals that are below 10 micron centimeters. But these are the values. We noticed that the films grown under the nitrogen atmosphere exhibited higher resistivity values. These are the XRD diffraction pattern acquired from the films under vacuum and here under nitrogen. And we could see that when we performed the deposition, we ended up with both BCC and FCC phases. Those films were deposited on silicon for some studies. For biomedical application, we use titanium substrate, and here are the patterns for high entropy alloys under vacuum and under nitrogen. To look at the density, we use X-ray reflectivity. We could perform XRR for thinner films, not for thicker films, because the surface was very, very rough. And an interesting discovery was the density was going up with the nickel concentration. This is the region of the critical angle from the XRR, and the position of this edge is proportional with the density of the film. Here is a table with the lattice parameters that we obtained. For example, for this film is T indicates the target, and then in vacuum and in nitrogen. And we see how the density goes up with the nitrogen content of the film. We use different methods for the concentration determination, XPS. This one shows how good the PLD technique is to obtain reproducible results, but also was used to capture the nitrogen to see whether the nitrogen is just embedded in the sample or is part of some nitrides. And the binding energy that is around 395 eV, it's a good indication that the nitrides are the nitrogen is in a nitride compound. That's the composition of the films with respect to that of the target. T again indicates the target. And so we have some up to 13% of nitrogen for this particular sample. But it's good to observe that the PLD transferred the stoichiometry rather well between the target and the thin film. We performed some mechanical tests, scratch, wear, to check whether the film are adherent, and indeed they are. And that's the coefficient of friction with a sapphire ball on the film. Because the films are not very thick, we perform also nano indentation, and we try to limit the depth penetration in the substrate. And what we notice is that by increasing the nickel concentration, we obtain higher and higher value, up to 15 gigapascal. And here is the friction coefficient measured with the diamond tip, and it's quite low. And also what we notice is that nitrogen films were a little bit harder than the films without nitrogen for the same nickel concentration. We perform electrochemical properties. These are for films deposited on titanium. So here are Nyquist plots. As you could see, there are not big differences between films with nitrogen and without nitrogen. And again, here is for both a Z plot. and both the phase plots of the films. Again, no big differences. And looking at all this data, we observed that the high entropy alloy N, nitrogen 6, was somehow the sample that showed the best characteristics, but what I want to stress is that all films display protective properties and anti-corrosion properties. Because the surface was very rough and with a lot of droplets, we explored films deposited by magnetron sputtering. And here are the images that are much better in terms of surface. And films, again, we look at the ion distribution maps, rather homogeneous compositions. Now we use different targets for grow these films, and because the surface was so smooth, it was very good for RBS analysis. And here you have a very nice plot where all the elements present in the film could be identified. That's a table with the results. Here we double the time from 30 to 60 minutes. The thickness is almost double. And we observe when looking at concentration that there is no preferential sputtering, so no enhancement in some concentration and depletion in the others. Here are two more compositions that we studied. So we added a lot of different high entropy alloy films. And here we test the biocompatibility of the films. And with respect to the silicon martyr, we see that cell viability is much higher on films with high entropy alloy thin films. And this could open the application area in biology, medicine, and so forth for these alloys. And here is the cytotoxicity of the films. And again, with respect to silicon witness, we see a decrease in cytotoxicity potential of these films. So these are some application of the films that we have in mind. I will move to the second part of the talk, the laser-induced damage threshold measurements for oxide films grown by PLD. We have in Bucharest a very interesting facility. It's a extreme light infrastructure called, that's the building. And inside we have two lasers. We see here one, and the other one is there. These are like soccer fields, football fields area, very big laser, actually are the largest in the world. And everything, what do I see here? This is the chamber where various interactions are performed and studied. Everything is big, but being big is also very expensive. Optical components, some very special mirrors could reach up to almost 1 million euros. So we have to understand how to use those things without damaging them. And the key word here also is if we have some predictive capabilities, it will be good if we could stop things before they happen. We use Langmuir probe and target current measurements, so electrical type of measurements, to measure the damage threshold, but also to see whether we could have some predictions of the optical coatings behaviors. These are the coatings that we studied, to the electrics that are used to fabricate them and were deposited by the PLD. This is the ISO standard, how it is measured classically. This LIDT, you could see that is rather complicated. Also by checking the reflectivity of a laser beam before and after damage on the coating, or doing some post-mortem in a microscope. You could see before, after damage, before, after damage. And also, you could look at the spatial frequencies in the reflected beam, and analyzing this, you can decide for what fluence you are below and above the laser damage threshold. But as you can see, these things are really complicated, and definitely these are not real-time techniques. That's what we want for our setup. So here are the details about the Langmuir probe. As you know, you are aware, there will be also a presentation on Friday about how this technique is used for laser plasma diagnostics. So the Langmuir probe records the charge that is expelled by the laser beam from the materials. And then we had this idea, if some charge is expelled, the sample, the target remains charged, and it has to extract some electrons to reach neutrality. And if we can measure that charge, which we call compensated charge, we can have ideas about how the laser interacts with the target. Here is the setup. That's the Langmuir probe. The output is connected to an oscilloscope, and this is the real experimental setup in a chamber that could be moved to different laser. We use a femtosecond laser here. So there is a movie here. And that's what we measure. Here are for hafnium oxide. We start from very low fluencies and we move to higher fluencies. And you see that the value of the charge current goes up significantly from somewhere below the threshold to above the threshold. And again, in nanoseconds, we apply these techniques. And when we plotted the average current versus the laser fluence, we obtain this behavior. And obviously, there is a region somewhere here and another one here. And the intersection point defines what's the laser damage threshold. That's the laser plume. I will not insist. Again, look at the scale, current below threshold and above. But even below threshold, these milliamps are easily detected. And so we get a good information about how the interaction proceeds. These were for nanoseconds. Here are for femtoseconds. Again, we could see that the charge above and below threshold could be measured, and important is to look at the plots. These are for femtosecond lasers, and we see that when we use the Langmuir probe versus target current measurements are more sensitive, but it's the same type of plot that we notice for nanosecond lasers. So it's something very general with the way the matter interacts with the lasers. Now we plotted the measurements according to ISO standard for 100 and 10,000 laser pulses. And we see that what we measure from one measurement here is below what we get from the standard, so higher sensitivities. And also we noted that this depends on the oxygen pressure that we use during the PLD growth of both hafnium oxide and zirconium oxide. So our next question was, what are the differences? If we plot XPS, they look almost identical, so we couldn't see anything. Better luck we got with non-Rutherford backscattering using a resonance for the oxygen. And looking at the stoichiometries, we saw that for low oxygen pressure, we got very close to the ideal 2 stoichiometry, hafnium oxygen 2. for higher oxygen. We've noticed that this was not the case, and this explains why we have poorer results for laser damage threshold from this type of coatings. Similarly, for zirconium oxide, the same behavior, same offset stoichiometry that results in not as good laser damage threshold. Now we plotted all these data. These are ISO data versus what we measure with Langmuir probe, and target current, you know, is just here. So it shows up, and the curves are according to this plot. So what we notice is that what we get in 1-2 pulses with the Langmuir probe or target compensation is what one would obtain for millions and billions of pulses, is the behavior of a mirror at an infinite number of pulses. So this is a very important result. We know this value from a very few type of measurements and not from years of measurements. But again, this shows that our method is very sensitive and integrates well with the classical type of measurements. So going one step further to the carbon foam targets for femtosensor, femtoseconds laser. Big experiments for this type of laser is to achieve protons with a very high energy that could be used in medicine for proton therapy. And here is an example of various groups all over the world trying to accelerate protons using the laser plasma. And it was in the first speaker mentioned the terahertz behavior of materials, and mentioned the plasma frequency, and that the fact that wavelength that is below and above could be transparent, could be absorbed. And again, for the femtosecond lasers, it results that the best electron density would correspond to, for a lossy material like carbon, which corresponds to milligrams per cubic centimeters, which is like 3 orders of magnitude lower than the normal electron density in a carbon film, like a diamond-like carbon or amorphous carbon film. So by using pulse laser deposition, but this time performed at a much higher pressure, we use either nitrogen, argon, CH4. We fabricated these foam samples. You see here a cross-section, and you see here a general SEM image of this carbon film. And according to TM, although we have some lattices here, it's a mixture of amorphous and nanocrystalline films. The density that we obtain, it's around somewhere from 10 to 20 milligrams. We have a lot of errors because it's very difficult to say what is the actual thickness of this film. But we tested this using Langmuir probe, and this is a nice result. When we have aluminum cover with the carbon foam, we obtain much higher charge and a higher kinetic energy. So it works like amplifying, and also here you could see, like giving a better coupling between the laser and the foam, and this will result in higher energy. Also this has been noticed right here in the damage. How many minutes do I? One minute. So let's, this is the target, and experiments were performed at Rutherford Appleton Laboratory with the Gemini laser, and Thomson parabola results. And this is the main result, that using aluminum cover with carbon foam, we obtain much higher protons energy. And that was my initial talk. I just want to mention that we are now doing some microwave discharge, and we ended up with these very beautiful nanoparticles, and we are open for collaboration. That's how it looks like, and we have a good characterization. And already we have an application like a paint that absorbs X-ray. And in conclusion, PLD is good for many things, but also sputtering remains very good. And we obtain good results for femtoseconds laser. We want to utilize the facility in Bucharest, and please remember that is an European facility, and everybody could apply for beam time there. Thank you very much for your attention. I'm happy to take any questions.
Thank you very much, Professor Kachun. The presentation is open for discussion. Please raise your hands who has any questions. Yes, please.
Thank you very much for a very nice presentation. And I didn't mention, did you measure the roughness of the deposited films? And
for high entropy alloy films, we measure the roughness by two methods, the normal AFM, and also from X-ray reflectivity for very thin films, it shows up. Now it depends, because the roughness of these films is the roughness of the substrate without droplets and the roughness of the substrate plus the droplets. So without droplets is very low, is below 1 nanometer, but with droplets it goes high up. But films grown by sputtering are much smoother, 1–2 nanometers roughness.
Okay, so, thank you. Because my second question was about if you applied the polishing before the nano indentation, but if the roughness is very good.
Yeah, our nano indenter can work as a scanning microscope. So first we choose a region, we take a map of the region, and then we decide where to do the nano indentation to avoid all those blobs and droplets and so on. So the results that I showed were performed on the smooth parts of the film.
I see. Okay. Thank you very much.
You are welcome.
Questions,
Thank
please.
you very much. Very nice question. I have a few questions. First, what are the costs for this equipment, for example, to measure lifetime? And the second question is, what kind of laser you use in this technique? Thank you.
Time of?
For example, to measure the lifetime at the femtoseconds range, what are the costs for this?
We do not look that much into cost, being a national...
but it is not cheaper, I believe.
Yes, it is not cheaper, but the cost is not our main focus. We just want to obtain results. For femtosecond lasers, we produce those mirrors in-house because a good femtosecond mirror is very expensive, and you do not want to ruin it, because in one experiment you have to go low, below, above threshold, and it's done. So it's hundreds of euros, one mirror. But we produce those mirrors by PLD in our system, and they work very well, and they gave similar results with industrial manufactured mirrors. So the cost was not a problem for us. Other costs, I don't know. Research is expensive. That's why I wanted to show you the last things with the nanoparticles. This is the very inexpensive research that we performed. That deposition with microwaves, it cost less than 100 euros to build that optical cavity with the microwave and to obtain a plasma on a metallic wire and then to get those very beautiful nanoparticles. That's the very inexpensive experiment.
But my question is homemade technique
yes,
or not?
Yes, actually it's made from a kitchen microwave. I work with some very good engineers. They took it from a microwave. They knew about cavities. We are with the laser, and if you take a class on laser, you learn about optical cavities, microwave cavities. So it was made by them from copper, and then a wire there, and that's it. Of course, transmission TEM is not cheap. But to obtain the nanoparticles, we were amazed. And you notice the quality. There are single crystal without defects, very, very nice. We are looking for collaboration for application, people that might have in mind things for these nanoparticles. Like in the previous presentation, there were some zinc nanorods. We recently started zinc. And during the vaporization, we got nanorods. So probably we will knock at the door of Professor Rusu with some nanorods and say, what about this? Could you do a measurement? He said yes.
Thank you very much.
You are welcome.
Next question, please.
My question is, you studied the optical damage of thin films. I remember one time the damage of bulk materials. What you can say the difference, bulk and films?
Yes, bulk it's very interesting, but the burning question at the Extreme Light Infrastructure Institute is for laser mirrors. And they have many very expensive experiments with very expensive equipment. And if you have a laser damage, you will damage the surface of the mirror, and the laser beam could go any places. And that energy will produce damage in any equipment or things like that. So they want, this is why I mentioned, the keyword there is prediction. So we can apply this to bulk materials as well. Actually, we did apply it for some targets. First, we started with some bulk targets. The zirconium oxide target that is 6 millimeter thick, and it works. But our interest again is on thin films, and when we look at below the threshold, there is a small increase. So you could calibrate your mirror, and you say, do not go above this value when you reach it. And
not about the theory, like just parameters, 1 joule, 1 nano, like parameters.
You want to know what we measure? So for metal 0.2 to 0.3 to 0.4, like a silver, freshly deposited silver or aluminum metallic film, joule per square centimeters. For hafnium oxide, zirconium oxide, we almost reach 1 joule, around 1 joule per square centimeter.
Okay, thank you. And the next question, you measured in nanosecond
femtosecond
domain and femtosecond.
Yes.
And you may compare, can compare.
Yes, of course.
I saw that 1 joule is the very frequent parameter, 1 joule per centimeter square.
Yes, but the mirror we have in mind that extreme light infrastructure are those big. And that laser delivers 200 joules, so it's well below 1 joule per square centimeter. Even for metallic mirrors, it's still okay because you have a lot of surface and the beam is spread. It gets more and more dangerous as you get closer to the interaction chamber where you have to focus the beam. But then you avoid, I don't know whether you had a time to see the intensity for Gemini when we irradiated a carbon foam was 10 to the power 21 watts per square centimeter. So there is no material that could take that kind of...
I understand. Thank you.
Thank you. I think we have to stop now here. And yeah, and I would like to thank the speaker again. And a few more nice announcements. So the next session will start at 11:50. So please be on time because we are a little bit late. The second pleasant information that the coffee break is just outside this premises, and it's waiting for you. And we would like to invite all of you right now to stay in this room, and we can make a group photo for the conference attendees. Thank you. And before we do that, a short announcement from the conference secretary. Nikita, please.
Hold on. Milest Wineries. So anyone who would like to join us, please address to the registration desk. Today by 12 o'clock we have to give the total number of people who are coming. It's for 5 o'clock. We're setting off from on 4 o'clock from here. So please. Yeah. Today. Yeah, today. Yeah.
Dear all, just I think we have to stay where we are. Just stand up, and maybe we a little bit get closer one to each other. Hold. All of our dear colleagues, please get a little bit closer. Closer, please. So we want to see all of us, and we can leave the discussion for later. It's a very nice. It's a traditional photo. If you look for the previous editions, so. So please do join the okay. Everyone is ready, so please focus on Konstantin.
with cheap and available zinc and tin, we end up in the castoreid type structure with a space group of I for bar and 4 different Vyakov positions for 3 anion. What is important is that castoreids, as well as all of the other structures I already mentioned, belong to the adamantine type family, and all of them can be viewed as a network of corner-sharing tetrahedra. But what in terms of chemistry is happening here? Because structure is quite flexible, it can stabilize a number of point defects, so we can have vacancies, we can have antisides, we can have interstitials, but usually we look in terms of chemistry at castoreid as a middle point in this triangular diagram of copper 2s, tin S2, and zinc sulfide, which is exactly in the middle. But as we have 3 different cations, we have copper, which means that our materials can be copper-rich, copper-poor. We have zinc, meaning we can be zinc-rich, zinc-poor. We have tin, again, we can be tin-rich, tin-poor. That creates an enormous amount of possibilities of how stoichiometric we can be. We have names for all of those scenarios, but here I will be showing you only one, which is a type of stoichiometry. So, for example, if in copper 2, zinc, tin, sulfur 4, we take 2 coppers out and we substitute it by zinc, we would create zinc on copper, and we would create a copper vacancy, because we would still want to have the charge balance happening. So if we take 2 copper 1 plus and substitute by zinc 2 plus, we would have this defect pair forming. And if you look at all of those defects, which are at least 3 types of vacancies, a lot of different antisides, we can also have interstitials, there are quite a number of calculations done for these materials, and we can see that there are 2 main types of defects. Those defects are usually separated in 2 big groups, one being the shallow defects. So they are normally benign, so-called good defects, and at the same time we have deep defects, which, for example, is copper on tin or tin on copper, and those are detrimental. So those are so-called bad defects. If those defects would be active, when we look at their concentrations, those would be enormous. We would be looking at 10 to the 19, 10 to the 20 defects per centimeter cube. That would be, in fact, structural disorder. How can we detect those defect levels? One of the options is spectroscopy. So, for example, we can do PL. But when we think about in terms of chemical and structural identifications, we would need to perform some X-ray diffraction. So, because when we have point defects, the scattering cross-section of the cation structural site is changing significantly. So X-ray diffraction would be, in fact, great if we wouldn't have zinc and copper in our materials, because zinc and copper, and if we have germanium as well, are first electronically similar elements, and second, copper plus, zinc 2 plus, and germanium 4 plus are isoelectronic, meaning we cannot really distinguish them, which brings us to neutron diffraction. With neutron diffraction, those elements are significantly different, and we indeed can distinguish those. So what is our experimental strategy? We start with synthesis of powder samples, which we are doing via solid-state reaction at different temperatures, depending on what our material is. We continue with chemical analysis, which we are doing via wavelength dispersive X-ray spectroscopy. That allows us to perform phase analysis, and also, as we are using elemental standards, to be very, very precise with the composition. We do make X-ray diffraction, but from there we cannot distinguish copper and zinc, and we perform neutron diffraction at this point in time generally all over the world, and combination of those two allows us to determine the structural parameters, the cation distribution, and the cation point defect concentration. We also do the UV spectroscopy in order to get the bandgap values for our materials. When we perform X-ray diffraction and neutron diffraction, we analyze our data using the average neutron scattering length analysis. And prerequisites here is that we have enough, meaning a lot, of homogeneous powder with a determined chemical composition. Those are absolutely necessary. Then we perform the Rietveld refinement. We calculate the average neutron scattering length of each of those sites. And based on that, we make a suggestion for cation distribution model. And we iterate in between those two in order to minimize the difference in between the calculated and the experimental average neutron scattering length of each of those sites, taking into account our composition. And this cation distribution model is what allows us to make conclusion about which type of intrinsic point defects we have, and we can also quantitatively calculate the concentration of those defects. So when we talk about castoreite solar cell absorbers, the first thing we are talking about is Kopot-Zink disorder. Why? Because when we look at castoreite, the ideal castoreite, we have our space group I4 bar, you can see it on the left, and we would expect copper onto A, copper onto C, zinc onto D, and tin onto B, which is not really happening. Because when we look at the real castoreite, more often than not, what we see is something what you see in the middle. We do still have copper onto A and tin onto B, but to C and to D have equal amounts of copper and zinc on copper antisites, which in fact are creating this Kopot-Zink disorder. And when we look at those defect concentrations, we are looking to 10 to the 20s, 10 to the 21s of centimeters cubed, if those would be active. How this Kopot-Zink disorder was discovered? The first hint was found via temperature-dependent measurements at the synchrotron. So it was found that there is a slight kink at in between 240 and 260 degrees C at the graph of the lattice parameters via temperature. Later, an order disorder transition was qualitatively described using Raman diffraction. And we also did this quantitative description of order disorder transition in Kopot-Zink tin selenide using synchrotron radiation. We also managed to calculate the order parameter. But can we see it, or can we see its influence over the optoelectronic properties? In fact, we do. Even when we take just UV spectroscopy on our powders, when we measure our material as grown, and we measure it when we temper it at temperature higher than this order disorder transition, and we quench from that temperature, it's shifting towards lower energy. When we allow it to slowly cool over weeks and weeks of time, we end up with material where band gap is shifting towards higher energies. There were also a number of reports showing the same effect in photoluminescence, and also there was a number of studies showing that annealing below this order disorder transition is in fact decreasing the Kopot-Zink disorder and increasing the VOC, in this way decreasing the VOC deficit. So that came up as a technology development. So such a post-deposition treatment brings us to decrease of Kopot-Zink disorder. But is there a possibility to avoid it whatsoever? When we talk about Kopot-Zink tin sulfur selenide, most probably no. But if we substitute part of this copper with silver, for example, we introduce 20% silver, we see a completely different distribution of cations in this structure. So we see zinc being located onto A, meaning that in fact that is not a castoreite structure anymore. We have stannite type structure where copper and silver are sharing the planes where before copper and zinc were. meaning that indeed we do not have any Kopot-Zink disorder. When we look at the bandgap energies in those materials and external quantum yield values, we see that also with introducing silver in the solid solution, we see a reduction in non-radiative recombination via defects. So indeed, it's possible to avoid Kopot-Zink disorder completely. What about intrinsic point defects? Here we had to verify if they indeed exist, we expect them to exist, and if they are exactly what we expect them to be. So we distributed and we've grown an enormous amount of powders in order to hit all of those stoichiometric points. We performed neutron diffraction on an enormous amount of Kopot-Zink tin sulfide, Kopot-Zink tin selenide, and Kopot-Zink germanium selenide materials. And we found that we do have this area, which is highlighted in red, of good defects in between A and B type of stoichiometry. So that is found to be the most favorable composition, where we have copper vacancies, zinc on copper, and zinc on tin defects. And also we found an enormous amount of bad defects in all other regions of this composition. So this indeed is a basis for defect engineering. When we look at total values for those defect concentrations, we see that the further we move away from the stoichiometry point, the higher those defect concentrations are. And that is, in fact, influencing our material a lot, because this variation in type and concentration of point defects brings us to the band gap fluctuation. In this way, also, the electrostatic potential fluctuations are there, and that decreases our VOC value, which increases the VOC deficit in its way. So optimization of the material towards chemical homogeneity is crucial in this way. And in fact, in order to reach the most recent record on those materials, that was one of the points which was indeed improved, the chemical homogeneity. But is there a way to avoid that whatsoever? In fact, there is, because not all of the solar cells have to be thin films. Some of them can be monograin. There is such a great technology where it's a powder, where every single grain of that powder is a single crystal. Those powders are homogeneous, castoreid-type single crystals. They have homogeneous chemical composition. It's a lot of them, meaning they're suitable for neutron diffraction. So we can enable study of structural disorder, but in the same time, from exactly the same material, working solar cells are done, which means we can directly correlate our structural disorder, all of our structural findings, to the device efficiency and performance parameters. And in fact, within one of our European projects, we did that. We correlated the structural disorder with PV parameters. We mapped a number of monograins in the AB types, so the most favorable compositions, with sulfur to selenium ratio of 0.6, which again shows us the most favorable band gap values to device efficiency. And we found correlation in between Kopot-Zink disorder and those parameters. But that is great. We have a nice material. We have a lot of findings. Can we apply any of that to any new materials? And in fact, we had a look at a completely new material, which is ternary nitrides. Those are earth-abundant alternatives to 3,5 compounds, so they are long-term stable. If you look at band gap energies and lattice parameters, they are comparable to the 3,5 compounds. So we are looking at zinc silicon nitride, zinc germanium nitride, and zinc tin nitride. They are simulated to be very efficient optical absorbers and emission with direct band gap. But as we are looking mostly at structural point of view, we were mostly interested in what is happening here in terms of cation disorders. And are those materials tunable by this disorder? So again, we run into the same trouble. We have zinc 2+, we have germanium 4+, meaning those are isoelectronic. So we do not need neutrons. And it gets even better because we have nitrogen here, which is a light element, meaning that there is just no way to avoid neutron diffraction. So in terms of structure, we have two possibilities here. We have Wurtzite type structure, which is having zinc element for disorder, which is just there. And we have sodium, beta sodium ferrite type structure, which has two different cation sites. So potentially it would be possible to have an order distribution of zinc and element 4, but it's not really happening. So could we experimentally get those materials with different degree of cation disorder? Yes, we could. Could we determine those structures? Yes, we could do that as well. We found that zinc tin nitride always adopts Wurtzite type structure. So zinc tin disorder is always there. And could we correlate that disorder with our band gap values? And yes, again, in case of copper zinc germanium nitride, we did. But what we find, by the way, is that in fact those are never pure nitrides. They always have a little bit of oxygen in that, at least when grown by our method. So again, we had a number of samples being synthesized using ammonolysis. We did vary temperature, time, cooling rates, and we checked if that would be influencing the disorder in those materials. And we found that in fact it does. And in the same time, that oxygen content is influencing the disorder as well. So in fact, we managed to find for every single pair of temperature and time, different values of order or disorder. So that is indeed changing depending on the conditions with which we are growing our powder. When we look at the dependence of the band gap, again, versus the oxygen content versus the order parameter, we found this kind of dependencies as well. As well, it's influenced by intrinsic cation disorder, but in completely different ways. Meaning that even when we have almost no disorder, that doesn't mean that we have the lowest oxygen content. Those values are specific for every single oxygen content or disorder. And when we are completely disordered, that does not depend on the oxygen content anymore. It becomes stable. With this, I would like to conclude. So I showed you quite some castoreid type compound semiconductors, which is at this point in time the only critical raw material free PV technology with the most recent world record of 15.1%. Those materials have structural disorder, different types. We have copper zinc disorder, and at the same time we have intrinsic point defects, which are vacancies, antisites, interstitials. Those determine the electronic properties of these semiconductors, and our findings allow us to give suggestions for defect engineering to improve the power conversion efficiency. For all of those, we did need neutron diffraction data, and copper zinc disorder is decreasing by low temperature annealing. In this way, we can increase the VOC values. We found the most promising compositional region, and we also had a look at ternary nitride, and we found that the band gap energy can be tuned by by zinc germanium disorder. With this, I would like to acknowledge all of my colleagues from the Department of Structure and Dynamic of Energy Materials at HCB. I would like to thank all of the former PhD students which produce those tons and tons of samples. I would like to thank all of the instrument scientists all around the world for their help with neutron diffraction experiments, all of the projects which we had in the meantime, and I would like to thank you for your kind attention.
So the paper is open for discussion, for questions. Any questions at the audience? Maybe I will start with the question. You show that you can understand disorder, but do you know how to modulate it to obtain the optimal efficiency of the solar cells? Or do you have any ideas how to advise big industry to produce good solar cells with testerists?
Yes, we have a number of suggestions which we can give. So the first will be to produce this low temperature annealing to give the material at least some time at lower temperature, because that allows us to decrease that disorder. In the same time, to look at a certain stoichiometric composition, so that only this kind of beneficial defects would be forming. And in my personal opinion, the key thing here would be to improve the homogeneity of the absorbable layer. I think that would be just really to avoid secondary phases, to avoid the inhomogeneities within the main phase. Which
is there any industry really interested in it, or you're just doing it for fun?
Industry, at least in terms of monograin research, industry is very interested with our result. We've got some amazing feedback as well, because we were working on materials which were produced by industry. So
the last question, do you believe in castorates or nitrites, or are you just switching to nitrate because you do not believe to castorates? So what would be the winner?
I believe in copper-based quaternary chalcogenides, which means it can be casterite, it can end up being a stannite, it can be any structure, but I believe that those quaternary materials hold quite some surprises for the future.
Okay, thank you. So, any other questions or remarks to the talk? Yes, over there.
Thank you. I wanted to ask, so the defects, disorder, it feels like it's always undesirable, or are they sometimes advantageous, or in some cases for you?
If it would be about castorites, I would say, first of all, it's always there. We really cannot get rid of it completely. So we can reduce it, but it's still always there. In case of nitrites, even having certain amount of disorder does not hinder the potential of the material. But that is still at a very, very different level of technology readiness. So that is still very low efficiency. It's still a very new material and still a new area of research in comparison to castorites. So we will still have to wait and see how disorder plays, which role the disorder will play in this case. It's too early to say.
Any other questions or remarks to this future of the photovoltaic?
Well, I have one.
Yeah.
Thanks for it's okay. What about perovskite? They also very high efficiency.
Yeah. Yes.
However, the disorder is also like another level.
Yes.
What's your opinion on that? Do you think this field will still keep booming, because it's really like booming right now?
You know, the more I'm part of those meetings, the more I start hearing the post-perovskite era. Post-perovskite era. And the more I hear it, the more I start getting this feeling that maybe there will be a post-perovskite era. I think perovskites are amazing materials, but they have to be stable. The material has to be stable. The device has to be stable, at least for some reasonable time, which is not the case at the moment. So once that is happening, I would say, yeah, perovskites.
Any other question? I still have one. Very stupid one. Maybe I was not listening to. But why silicon is not present at the Earth? Why people do not continue with silicon? You want to have high efficiency or what? Because you have a lot of silicon there.
Silicon is great. Silicon is the most mature technology we have at the moment, but it's expensive to produce it. At the moment, yes, the prices for those solar cells went down significantly, but
it's earth abundant.
The material, yeah, of course, yes. Silicon is absolutely earth abundant. That was never the question. That's never a problem. Cadmium is toxic. That's a bit forced. But in terms of silicon, it's more about how much silicon we would need and the production of it, which is very high temperatures.
Very high temperature that increases the cost, right?
Yes, significantly.
And your materials, your nitrides or other stuff, are cheaper or easier to produce? Or?
First of all, we need much less of it. It's a thin film. Second, the temperatures are always lower than silicon, just always. And when we talk about thin films, I think there will be a very nice talk about it on Thursday, about the recent advantages and records, in fact, in thin film castorides. And there they're using temperatures not over 500 degrees, which in comparison to more than 1,000 for silicon, and also the question of times, how much time it takes at that temperature. So
Okay, thank you very much once more for the speaker. So now we're at the subject that I do not know anything. I give a voice to the colleague from
Thank you, Vladimir. Firstly, I'd like to really thank the organisers for giving me the opportunity to come here today and speak with you. I'm genuinely excited. I've never been to Moldova before, and so I'm really happy to be here, and I enjoyed the little history lesson that started us off. In terms of ground rules for my talk, I am a native-ish English speaker in that I'm Scottish. So if I get a little bit Scottish or a little bit fast, please, can someone just slow it down? Wave. That would be great. Okay. Yeah. Okay, so I'm going to talk to you about spatially resolving superconductivity. This might be a little bit controversial for some of the members of the superconducting community and a bit trivial for some of the members of the material science community. And that's just the way the world is. I'd like to start by giving you my take-home message. Microstructure matters, and this is even more important in quantum materials. I'm going to suggest to you that conductive atomic force microscopy is a good way of characterizing superconductors. And I've left this in grey as a little bit more of a discussion piece that type 2 superconductors are heterogeneous, inherently heterogeneous. And so far I have had 4 crystal growing colleagues who've all given me very high quality, quantifiably good single crystals. They are all heterogeneous on the micron scale. And so this seems quite inherent. And that'll actually be one of my finishing points, that our equipment is currently down, but if you can provide me genuine evidence that you think your type 2 superconductor is homogeneous, I'm happy to measure it, and I will be happy to wager you a beer it's not. Okay, so why spatially resolve conductivity in superconductors? What's the point? Superconductors are defined by zero macroscopic resistance and the Meissner effect. Okay, so I'm looking to see something like this. Can you see the mouse on the screen? No, okay. So I'm looking to see zero resistance. It should be a step transition. I'm looking for the expulsion of magnetic field, and ideally I'm looking for peak in specific heat. Right? That's a nice macroscopic phase transition. The challenge is that we're going to start from right to left. Specific heat. At these temperatures, you can calculate the volume fraction of a superconductor from specific heat, but that's actually only the volume fraction of the electronic conducting material that goes superconducting. If I put an insulator down there, that wasn't affecting the specific heat. And so it doesn't, that whole specific heat argument does not work for insulators. The Meissner effect, that's really good, but you actually have to be very careful about how you calculate the screening. It's not as trivial to interpret as is often done in the literature, and I can give you a reference for this where some Campbell in the 71 just wrote a paper being like, stop using Meissner, or if you do, be very careful. So, superconductivity, we're left with macroscopic zero resistance. This is the property that defines a community. This is what we want. It has a challenge. If you use 2-probe, you measure the contact resistance from your electrodes. Solution, 4-probe. This is where the challenge arrives. 4-probe resistivity requires the assumption of homogeneous electrical conductivity. There's no way around this. If you measure 4-probe resistivity, you have made this assumption. Okay? And that's where it actually becomes very important to spatially resolve the conductivity to find out, was that a good assumption? Now, I'm currently having a free and open exchange of ideas with some reviewers in Nature Communications about whether this is true or not. It is. You can read the papers, you can read the literature, but one of the things I want to say is that current techniques do not spatially resolve conductivity directly. You can indirectly resolve it in many, many ways. I'm going to say ARPES is a beautiful way of getting band structure. And now you can get nano ARPES, so you can look for a gap state of your superconductor. That is not a conductivity measurement. Scanning tunneling microscopy. You measure the local density of states. That is not a conductivity measurement. You can do scanning squid. You can put a current through and you can measure the stray magnetic fields and get a current. That is not a conductivity measurement. I'm sorry if this seems obvious. It's not obvious to my reviewers, and so I'm quite keen to make it very clear the differences. Now, what I'm going to do, I would like to, having told you what is not a measure of conductivity, I'm going to tell you how I do measure conductivity. And then I'm going to give you 2 example materials. I have more, and in many cases you can just ask me questions. I've got quite a lot more slides. CAFM. It's a contact mode technique. I like to describe it as having a very fancy multimeter. I raster across the surface of my sample, and I measure the conductivity. How do I measure the conductivity? Specifically with the circuit like this. Okay? And so I am doing 2-probe conductivity measurements, and I can get very good, 5 nanometers lateral spatial resolution, and probably in the picoamp current ranges. The critical thing here is I cannot tell you the absolute value. I do measure electrode contributions. I can measure changes. And so the power of this technique is to go into the superconducting phase of a previously homogeneous crystal and look at how that phase is. Okay? This is my material I want to spend most time on. Iron silicium tellurium. It's quite popular in the superconducting community right now because it's got a number of exotic phases and reports. And I'm going to try and show you the multi-scale potential. So rather than just taking macroscopic or nanoscopic, I'm going to take you down through the length scales. Before I do, I'll give you a little bit of background. So there's a lot of papers, Nature materials, Nature physics, science, whatever, looking at, for example, the crossover between Bose, Baudin, Cooper, Schiff, and Bose-Einstein condensate, theories of superconductors. So that just means you've got different statistical regimes, and looking at the macroscopic properties, this superconductor is meant to be bang in the middle. You've got zero energy vortex bound states, which are inherently exciting just for potential applications, same for 1D Majorana channels. You've got a nice review here to show you that. I put this review here because it's a bit older, and if any of you have come across the nickelate recently, there's some reports of coexisting superconductivity and magnetism in there. The same thing is true of the iron compounds. I think it's generally agreed it's not true in the same phase. Okay, so all I want you to get from this side, it's a very topical material. There's a lot of interest. It's been very, very well characterized. Now, macroscopic characterization. This is resistivity of crystals from the same batch I used. This is actually grown by Vladimir. He's identified TC as 14.5, which is, I think, here. Other people have reported the maximum TC of 14.8, which is here. And I hope you can get from, sorry, you can't see my mouse. Vladimir is called the middle of the transition TC. Other people have called the start of the transition TC, and that is the only reason this isn't a highest reported TC temperature. Okay, so this is as good as single crystals get for this material. It has a very low residual resistance and has linear behaviors above the macroscopic superconducting transition. It completely expels magnetic field Meissner effect. So you see that, it's a big curve. If you do it in field, you get the pinning, but it's still a Meissner effect. You can do specific heat. I think, I actually can't remember the volume fraction for this, but I think it's 2.7 instead of 3.4, 3.4 being expected ideal, but it's a good macroscopic specific heat. You can do MH curves at 2 Kelvin. Again, this is exactly what you expect for superconductor. So, we can say, from macroscopic measurements, there is no reason to say this is anything other than a homogeneous superconductor. I'm going to skip the volume fraction calculation and specific heat, but if you're interested, you can just ask me about this later. This is now going into what's new in some of the work I've been leading. This is a scanning electron microscope image of the sample surface. There's no obvious second phase. It looks like a fairly well-cleaved crystal. If you look at CFM at 2 Kelvin, you see no current. None. So I've just got my crystal, landed on it, cannot get a current. Solution, CFM, you move around the surface. I think this is a 30 micron scan area, and if you move around the surface a lot, you can eventually find this area with enhanced conductivity. So here the yellow colors are high background conductivity, the blue colors are low background conductivity. What I hope you can see and agree from here trivially is the sample is heterogeneous. The conductivity is heterogeneous, and so that whole assumption about 4-probe resistivity is not relevant. The other thing I would guess, I'm showing you this image to show, is we actually scanned, I think it was nearly 500 microns square. This took months of finding insulating areas before we found an area which had conductivity. So despite all of that really nice data, despite this being among the best reported properties of this family of crystal in the literature, it's actually only got a tiny amount which has enhanced conductivity in CAFM. Now, I cannot tell you it has zero resistance because I measure with electrodes. So I have to look at other ways to say, okay, how can I say it could be a superconductor? 3 things: temperature, magnetic field, and current. I cannot use large currents in my setup because an AFM is effectively a beautiful fuse with the tip limiting any currents you can go. So that's just not going to work. I can look as a function of temperature. So the first image I showed you, this was a 2 Kelvin image. I'm now showing you one at 8 Kelvins, about 10 by 10 box. As I increase in temperature to 20 Kelvin and 30 Kelvin, you see local areas of conductivity which eventually vanish. Now, these areas of conductivity we're going to come back to later because they actually fluctuate. So what I mean by this is when I do CFM, I take conductivity in both directions, and it's a standard test, do you have a real signal, is does it look the same? And the answer at 8 Kelvin is, yeah, it's the same. We've not changed it with the tip. It's good. At 20 Kelvin, I still see dots and isolated islands of massively enhanced current, but it's always in different places between forward and backward scan. And so that's suggesting some kind of fluctuating order parameter rather than a metastable phase. 30 Kelvin, it's completely gone. And of course, you take it back down in temperature, 8 Kelvin. We have the very, very similar structure. A slight modification here, likely just due to vacancies. It's a known thing in AFN. Okay. That's the best proof I can give you because we didn't have access to magnetic field in this setup. The other thing I can talk to you about is a gap state. Now, I'm not sure the background of people in general, but I'm going to explain superconductivity incredibly crudely and tell you that you have got electrons near the Fermi surface, and if those pair up to form Cooper pairs, they leave a gap where they came from, and they go as form a Bose-Einstein-like condensate in the lowest energy states. So you have this gap where you expect electrons, but you do not have electrons. And in scanning tunneling microscopy, measuring this gap is a normal way of saying it's a superconductor. We can do that. The technical limitations, we could only do it with a positive field. This is a little bit equipment development. But what I hope you can see here is it's completely flat and linear. There's a stepwise increase in current, and then a second changing gradient with a much higher increase in current. That is strongly suggestive of the fact that this is a multi-band superconductor. And so you might expect two changes in gradients, exactly as we have here. I've done DIDV below it. We didn't have an opportunity to measure with a lock-in because we're doing equipment tests of principle, and so this is genuinely a numerical differentiation of the raw data. And so given that, it's actually quite high quality, but I appreciate it looks a little noisy from here. So I have enhanced conductivity that vanishes above TC, is associated with a gap state. I cannot prove to you it's a superconductor, but it looks a lot like one. Now, why does this matter? So in this case, we didn't trust our data. Fundamentally, it seemed like it was too new, it was too big, we were unsure, and so we started looking to see why we might have these changes in conductivity. The first thing we did is scanning electron microscopy and energy dispersive X-rays, and here you only see potentially the smallest hints. Okay, it's not obvious, but it would explain why no one else has reported it before. Luckily, we have some nice collaborators out in Imperial who have access to atom probe tomography, and so we can do very high compositional mapping. And so when we do that, we find actually the enhanced conductivity area has a second phase. So you see the 2 dot there, that's a bottom graph, and the 1 dot, that's a needle from the top graph. And I think very uncontroversially, you can see that these have different compositions. So there's two things. Firstly, we can see a difference in composition, so that does explain why the superconductivity is isolated. The other thing is we couldn't see it in energy dispersive X-rays, which is perhaps why it hasn't been reported before. And the third thing, rather ironically, is that the superconducting area actually has a different composition to the target phase material. So target phase material is Fe Se04 Te06. This is what's reported in the literature, this is what people do. And if you just take an area of the bulk, we're fairly close to that here. Okay, so graph 1, that's fairly close to target composition. That's actually an insulator. If you go to superconducting, the minority phase, that's closer to iron 1, selenium 1, tellurium 2. So a completely different composition. And that's one of the things I want to show from this, is that actually measuring locally is important for your assumptions, but it's really important to know what you're actually measuring. Yeah, okay. A little bit of new science. I mentioned at the start it was in the crossover regime. This is largely a theoretician's interest rather than my own. But you see here the homogeneous conductivity. As you increase temperature, you get these dots. This is consistent with preformed pairs. You get zero conductivity above TC at 30 Kelvin. This is important, this family of materials, because pseudo-gap properties are hard to measure in multi-band superconductors, in that this hasn't been measured before. It's a theoretician's expectation, and there's been some really nice work indirectly associating it from R pairs and how it might look, but here we can use CFM to directly measure those preformed Cooper pairs. So that's, I would say, quite a big deal. This is a list of the new science we can get from the CFM for this system. I want to move on because I want to show you another system. So this is another iron-based superconductor. This one I got hold of because it had interesting microstructure, and it's known to have interesting microstructure. Again, starting, we have a macroscopic TC, this is about 33 Kelvin. Again, this is one of the top you can get for this composition of material. We're expelling, so there's resistivity, you can move that transition with the magnetic field, you can have the zero field expulsion of the magnetic field, and again, 32.4, there's TC. Interestingly, if you were to measure this with using terahertz and look at the gap, they actually see no change in their gap at macroscopic TC, and it goes to a much higher temperature. And so that was when we were a little bit interested, like, ooh, where did this microstructure superconduct to? I now have access to a magnetic field, so I've gone below TC. I see the white colors here, massively enhanced conductivity. You can see it's a detailed and rich microstructure. I can go to 45 Kelvin, and you see the volume fraction has changed significantly, but you still have this highly conducting microstructure. If I were to apply a magnetic field of 5 Tesla, I can get most of it to go away, but not all of it. If I was to go to 55 Kelvin, so take the field off, heat it up, the microstructures come back. And if I apply another 5 Tesla field, I can make it go insulating. So in this case, we see that the magnetic field can kill this enhanced conductivity, as one would expect for a superconductor. But the superconductivity is locally stable, where this is 55 Kelvin, TC is 32, 33 Kelvin. So really significantly above, which leads to the question, how far above? This is my macroscopic resistivity curve. First stated 2.5 Kelvin, 10 Kelvin, 55 Kelvin, 65, 75, 85, 105, 125. It actually looks like we have a little bit more conductivity here, and then 150, finally, it's mainly gone with only a few little dots. This 125, so big picture, conductivity locally, very, very far above macroscopic TC. If you look at the microstructure and you see these islands, that's perhaps not a shock to you. Like, all I'm saying is, if you measure lots of little islands with a 4-probe technique, you get a very different answer to if you measure locally. Microstructure matters. One of the things that always interested me is why at 125 it appears to strengthen before it vanishes. I don't know, but the same thing has been seen in the Cooper rates, where they see the pseudo-gap and the gap states seem to get stronger just before they vanish. And so it's one of those moments where it was a little bit relaxing to me to know it's not just me who doesn't know, it's just a weird thing. Okay, and a little bit of ARPES data. This isn't mine, this is on the same nominal composition, and you can see that they have this, I can't remember exactly what they called it, but we went to some length to not call it a pseudo-gap. You see that the band structure is actually pretty continuous between 10 and 35 Kelvin, so the top 3 graphs. Then you should have the transition temperature. Band structure doesn't care, and it continues up to they've given between 125 and 150 Kelvin. And so that ties in pretty much exactly with what we have seen in CAFM, suggesting that actually this family of iron-based superconductors has a much higher TC than previously reported locally. And so I think that's one of the things that I find very exciting and very interesting about this work, is it's implying that the macroscopic transitions and measure we report, firstly, they're not relevant or valid. If you have a 4-probe measurement and you have a heterogeneous conductive landscape, that 4-probe data doesn't mean what you think. And I tried to find a bit more about that, but it's actually very hard to make any good general statements without knowing your exact microstructure, because it matters where it is in between the electrodes and how it dissipates the fields. But locally, we seem to have conductivity to really quite high temperatures in the materials we've looked at so far, in slightly surprising compositions and phases. And so with that, I would like to thank all of my collaborators. Without them, this work is not possible, particularly the crystal growers who are kindly in this room. And I want to actually shout out to them, because I say I've measured these properties on, I think, materials from 4 different growers. Not every grower will let you stand up and say that single crystal isn't quite homogeneous. So I can't share it all. And so thanks to these guys for, just going after the science. And thank you for your attention.
Thank you very much for a nice talk. Please, questions?
What is the information depth of this method? And the answer is it depends what you're measuring. So if you're measuring a dielectric, you have typically it goes a couple of the tip radiuses into the material. If you're measuring a metal, it should be perfectly screened, so it should be in the surface layer. If it's a superconductor, you should not see into the surface. So it's actually, it depends on the material, and it depends completely. I would like to know which technique you have that does show the volume of the superconductor, because magnetic fields quite famously don't go in, as neither do electric fields. If you're asking, is this a surface effect, one of the things I can do is I can scratch away the surface with the AFM tip and see how it changes down. And I can tell you, I think it was went 10, 15 nanometers down. It's like, yeah, it's the same. So.
Okay, thank you for your fascinating presentation. And 2 related questions. First of all, what is the spatial resolution of your map? Which smallest features can you observe your CAFM?
So this is a really good question. We cannot compete with scanning tunneling microscopy. We are limited by the radius of our tip. We have tips commercially available down to 5 nanometers in size. You can see enhanced resolution, or you can see changes on an order of a couple of nanometers. The scans I have shown you don't have that resolution because we found the properties were on micron scale. So here I'm typically using about a 40 nanometer pixel size, but that's just because at the length scale I see the changes. I can zoom down to a couple of nanometers.
Community really need such methods which would allow to see inhomogeneities of superconductivity at the scale of 100 nanometer object, that is, of the order of 1 nanometer resolution.
So you say that, and I think I have a slide here for that. So this is actually some data that's come out last week, and so you'll forgive the screenshot from the student. This is BISCO. This is a homogeneous classic superconductor, and it is heterogeneous on the 5 nanometer charge density wavelength scale, but it's hugely heterogeneous on a 40 micron scale as well. And so the question is, which length scale do you care about? I would argue you have to know about both.
Thank you very much.
Thank you. I just, on the quick nanoscale, I'll quickly tell you, this disordered superconductor, yeah, you can imagine this as an array of Josephson junctions and get oscillating currents. I would love to talk to you about that later in terms of simulating.
So just as a curiosity, did you take any standard superconductor and try to use your method to prove it is heterogeneous or homogeneous or, well, again, you are probably already answered the question. Like,
which material do you have in mind for your homogeneous?
I know, textbook semiconductor, superconductor, something which is like really known and
so Newtonian, niobium.
Yeah, for example.
Niobium,
yeah.
Sorry. Yeah, so the AtoCube, the equipment guys have done this and they see it and it works. We've been trying to do it, and it's one of the reasons because I'm looking at the type 2 superconductors and focused on that. Yeah, we just look at the changes, but it's also been done on a type 1 superconductor. Two of the crystals I have done have been to prove it works in a standard homogeneous system, but the type 2s, I would bet you a beer, are not homogeneous.
Thanks.
Thank you very much. Thank you very much. And the last talk will be given by Dr. Makarov, Denis Makarov from Dresden, Germany. Please.
Thank you very much. Also from my side, good afternoon. It's a pleasure for me to be here. It's a pleasure for me to have this opportunity to present our activities on curvilinear magnetism, which we are doing at Helmholtz Zentrum Dresden-Rossendorf. It's in Germany, in Dresden. And as you can see, we have a pleasure to collaborate with a great amount of different groups worldwide. And I'd like to use this specific possibility to also advertise what we are doing, and hopefully there will be some interest from your side. Maybe we can start also collaborations with a group in Moldova. So what we are in principle interested in something what is also very close to activities at Institute of Applied Physics, what we discussed yesterday with Professor Surkan, and this is antiferromagnets, especially collinear antiferromagnets, like what you can see here. It's a chromium oxide. It's a magnetoelectric collinear insulating antiferromagnet. And what we are interested is a distribution of magnetic order parameter in this material, which I will refer to as a magnetic texture in my talk. So basically it's a spatial distribution of a magnetic vector field or vector field of the order parameter in this material. And what we're interested is how the magnetic texture is changing when you're coming to some defects, for example, to the surface or to the boundary. So for example, how the magnetic domain wall is evolving in such kind of material. And interesting here is the lowering of symmetry, which you will have, for example, from the bulk of the material closer to the surface, where you have a symmetry lowering at the interface or at the boundary, and how does this change the collinear antiferromagnetic order in the material. This can be done in single crystals, it can be done in thin films. Thin films also have additional very interesting appealing point, because they can be fabricated in an integrated way. So kind of you can structure your thin film, you can integrate electrodes, you can basically gate this material, and you can investigate what will be happening with this material if you apply magnetoelectric fields. And in this case, you can also explore, for example, the magnetoelectric random access memory type of application examples. So in my talk here, I will discuss very specific way of lowering the symmetry, where the surface of material will be geometrically curved. So in principle, everything will be given, the physics will be given actually by the change of the shape of the object. So roughly speaking, what we will discuss, it's low-dimensional magnetic structures where you have like a nanowire or thin film, and what you do, you just geometrically curve this material. And a very simple question which we want to answer is how the physical properties, how the responses of this material will change if you will have this curvature. Before I will continue, my talk will be exactly about this type of fundamental effects, but just for completeness, I want to mention that there are a lot of very beautiful activities where you can apply this geometrically curved magnetic thin films. For example, you fabricate them on flexible substrates or even elastic substrates. And in this case, you can apply them, for example, for sensor research, for human-machine interfaces, or I don't know, soft robotics or some kind of application. It's a beautiful type of research by itself. And if you're interested, I'm very happy to discuss it afterwards. I will start with this slide. There is a review paper by Paola Gentile and Carmine Ortiz, which in principle tells you that effects of curvature is not specific to magnetism. Of course, it's different types of soft matter systems. Again, we will not address them, but also all types of condensed matter systems actually benefit from effects of geometrical curvature. It can be superconductivity, semiconductors, topological insulators, 2D materials, and of course magnetism. Before we dive into the discussion, I would like to acknowledge that there are two types of effects, like families of effects, and one of them is a quantum effect. This is something which will be addressed much more in the workshop organized by Vladimir Fomin, where exactly the Fermi wavelengths is comparable to the characteristic size or dimension of the curvature. So very, very small curvatures will have very interesting interference effects where you have a lot of impact on wave functions. For example, like analog for condensed matter of Aronov-Bohm effect, Aronov-Anandan type of effects, and these kind of things. So if you're interested in such kind of effects, I'm only able to advertise the symposia by Vladimir Fomin. There is another effect, which is classical effects, and this is exactly what will be discussed in my talk. In this case, what you have is a curvature which has a characteristic size, which is much, much larger than the Fermi wavelength. So in this case, everything what we will discuss is the effect of geometry, how geometry actually impacts magnetic or any kind of other properties of your material. And as this is a classical effect, in principle, this is a generic effect. So it's valid for any type of material. So I would like to illustrate it with a very simple example. It's a Hall effect. So Hall effect, it's you have air conducting material, semiconductor, metal, doesn't matter. You push currents through this material, and then if you have, for example, means to bring time inversion, then in this case you will have a Hall effect. You measure transverse voltage by pushing the currents through your conductor in a magnetic field. Very useful effect, very well-known effect, but there is a very interesting trick what you can do. You can just take the same conductor and you can switch off the magnetic field, and in this case you will have time inversion preserved, but if you will have an arc-shaped object, you will have, for example, non-centrosymmetry in a material. So now if you will have non-centrosymmetric material, again, you're lowering symmetry by the geometry of this material, you will force the carrier, can be electrons, can be holes, to move on a circular path. And in this case, if you will do a little bit of electrostatic calculations, you will see that in this geometry, you will also have a transverse voltage emerging, but this transverse voltage will be proportional not to the current, but proportional to the square of the current. And this is a very beautiful thing, because in this case, if you will have an even harmonic, so basically you will have possibility to observe this effect on a second harmonic. And if you will have even harmonic, you will be able not only to upconvert, but you can also rectify, right? In this case, you can use it in any material, because again, I would like to emphasize that this is a theory which is not specific to the material. So this is a beautiful example of the work from US, where they took graphene. You have to gate appropriately the graphene, but in this case, in a log-log scale, the transverse voltage as a function of current which you push will be a nice, beautiful linear curve. It's actually parabola if you will plot it in a linear scale. As the effect is not specific to the material, you can basically take any other material. So this example of bismuth, Bismuth is a higher order topological insulator, which has very interesting surface states, very interesting conductivity. And what you can see here, that also on the second harmonic, the graph in the center, I have no mouse, but in the center you can see also a parabola. So basically you measure transversal voltage as a function of current, and there's a quadratic dependence. Okay? The frequency for transport measurement, usually it's in a range of a couple of hertz, like 100 hertz. But now what is interesting, that the effect which we explore here is called nonlinear Hall effect. It's a frequency, in principle, not specific. So it's not like in semiconductor where you have terahertz gap, what we heard today, but you can simply go and do up conversion also at terahertz frequencies. So basically on the right-hand side for you, you will see arrays of such kind of arc-shaped structures which basically break space inversion in the material. And what you see here is also second harmonic generation. So you will have, for example, possibility to up-convert to third harmonic, fifth harmonic, like odd harmonics is trivial, but also a second harmonic. So you can also rectify, for example, at terahertz gap with bismuth as a very simple magnetic or non-magnetic, basically conducting material in this specific case. So everything what we discuss here is actually effects of geometry. If you will think about magnetism, there is a zoo of different structures which you can fabricate, and there are a lot of activities worldwide where people develop different means how to fabricate structures which are geometrically curved. They're beautiful activities. I will not even try to address all of them, but it's you can think about anodization templates. You can think about some different curvature templates where you can, for example, use magnetic thin films which are deposited on these templates. Or, for example, you can use direct writing. Focused electron or ion beam induced deposition allows you to fabricate different type of structures also on sub-micrometer scale with a geometric curvature. There will be a very interesting talk tomorrow by Rudolf Schäfer about how to study such kind of objects, because in this case, the object is three-dimensional. So you have to see actually not only on the top surface of the object, but also on the back side. So you need a tomography. In this case, you can use different types of tomography, like electron holography or X-ray tomography. But of course, standard methods like magnetic force microscopy or magneto-optical Kerr effects, it's something which is very, very useful for this characterization. So in my case, what I will focus now on is actually the physics behind what you measure in this type of structures. The physics is actually very beautiful. The physics is developed here by the group in Kyiv. This is Professor Heidi Day and Professor Sheka. Yuri Heidi Day unfortunately passed away a couple of years back. But the idea behind it is very, very straightforward. If you will have a magnetic vector field, for example, ferromagnet, but in principle for statics, you can have antiferromagnetic energy functional also in a very similar shape. So what you do, you basically recover, do a geometry transformation. You have to transform coordinate frame in order to recover the space invariance of anisotropy. So in this case, and there is a very unique transformation. And this transformation basically, as usually in analytical geometry, it gives you two potentials. Can be scalar potential, vector potential. In magnetism, we name them anisotropy and chiral interaction, so or Zelashinsky-Murray interaction. So basically what you see here that in this energy functional, if you will rewrite it in a coordinate frame where the anisotropy recovers its space invariance, you will have the energy term which is proportional to directional cosine of magnetization squared, which is in principle magnetization squared is anisotropy, and you will have a term which is shown here in the reddish color, which has a very interesting symmetry. It's a kind of Lifshitz invariance. It's more like a magnetization times square of magnetization, so such kind of terms, and this is a chiral interaction. So basically the take-home message here, as soon as you have a thin film or nanowire, which you geometrically curve, this object will necessarily exhibit additional responses, and this is anisotropy and chiral interaction. So this is exactly what is the take-home message here. And if you know this, you can already start quantifying them. So for example, here what you see, it's a parabola. It's a very simple experimental realization of the object which is not straight. Still, it's a planar object. There is no kind of three-dimensional curvature, but it has a gradient at the apex of parabola. And at this apex, you will be able to have the gradient of curvature, which is the same as a gradient of chiral interaction. Chiral, this Zelashinsky-Murray type of interaction. And what is interesting that the domain wall will be pinned there. So you will have a chiral domain wall. There will be a little bit of degeneracy in the type of domain wall, which can be stabilized at this apex and things like this. So if you will check the Zaleshinsky-Murray interaction strengths at the apex of such kind of very simple couple of micrometer large object is actually sizable, comparable to something what people do in skyrmionic research. And that means that in principle, if you will take this idea, you can also be able to fabricate magnetic thin films with curvature, with sufficient curvature to generate skyrmions or chiral domain walls or skyrmion bubbles based on curvature effects only, right? So you can work with very conventional materials like permalloy type of or cobalt platinum without any kind of space inversion symmetry breaking with curvature, which will give you chiral interactions. But the beautiful thing, so in this case, you don't need to know anything about non-local interactions. So everything where you have exchange, anisotropy, Zaleshinsky-Murray interaction will be perfectly sufficient to describe these objects. But the beautiful thing comes if you will take into account also non-local interactions. So basically the rich aspects of magnetism is exactly where you will have all the different microtextures like domain walls. This comes from non-local interactions, and this was a very interesting discovery by Denis Shek, Alexander Pilipovsky here. What you will see is, if I will just make a long story short, you will be able to find in energy functional, which will have also a non-local interaction, such kind of terms which are shown here in a bluish or reddish color. And these terms, if you will see, these terms are coupling, like, I don't know, now terminology is actually a little bit loose. In magnetism, we use the language of magnetostatic charges, like surface and volume charges. These are some fixtures charges which we, in magnetism, basically use in order to describe complex magnetostatic interaction. These charges, usually in the planar thin films, they do not interact. Okay, this is not forbidden by symmetry, it's allowed, this interaction is allowed, but in a thin film, which is planar, you have a mirror plane, and the mirror plane cancels the interactions. In the sense, it makes it trivially zero. As soon as you will have a curved thin film, there is no mirror plane anymore. So basically this coupling between surface and volume charges becomes not only allowed, but it becomes finite. Okay? And this is exactly the bluish and reddish terms. It's exactly the coupling of volume charge and the surface charge. And if you will see on the integral, in the kernel of the integral, you will have the term which is 1 over distance. So this is essentially non-local term. And at the same time, this term also, now you have to simply trust me, it supports chiral symmetry break. And it's non-local. So now we have a very interesting prediction that there is a expression which is linguistically correct, non-local chiral symmetry break. Now the question is, what is the physical consequence of this non-local chiral symmetry break? Idea here is very interesting. So basically, if you will have an object which has a magnetochirality, the simplest object with magnetochirality would be a vortex. So basically you have, let's say, a nanostructure, disc-shaped nanostructure, and then a soft magnetic material. Magnetization in this magnetic material will just curl, fill in the boundary. This is exactly where boundary comes into play. And at the center, you will have divergence of magnetization because the vector field has to be continuous. It kind of has to go up. And this is what is called the Bloch line, right? So this red thing is a Bloch line. Now, if you will make the surface, bottom and top surface, non-equivalent, then there will be a very interesting consequence of this. If the symmetry of this top surface is sufficiently low, you will be able to have a bend of this Bloch line, but it will also twist. And the twist of the Bloch line will be chiral in this case, and it will be coupled to the magnetochirality of the vortex texture. So basically, a non-local chiral symmetry break induces two magnetochiralities in the same object and couples them. So this is a physical consequence of this cryptic wording or expression of non-local chiral symmetry break. You can also see it in experiments. So yeah, I show usually like cartoons here because they're a little bit easier to understand, but there is a lot of experiments behind it. So what you see here, it's a cap. It's a permalloy cap, like 50 nanometer, 80 nanometer cap. So you need sufficient thickness of this magnetic material on the spherical shape. The top and bottom surface you can reconstruct in electron tomography. As you can see, they are very much non-equivalent. You can do electron holography in order to see the magnetization vector field. So you can see indeed a very beautiful vortex here. And now you can combine electron holography and micromagnetic simulations in order to confirm that indeed the Bloch line here, or the vortex string, depends how you like to call it, is indeed a space curve. So basically this thing is described by curvature and the finite torsion. And indeed, it's coupled to the magnetochirality of the vortex texture. So in this case, you have geometry which you use in order to basically manipulate magnetic texture, right? Now you can do a step further if you have it, and then you can ask a question. Okay, the geometry is very obvious, the curvature is very obvious, but geometry has also topology. And topology can be trivial or non-trivial. Trivial would be thin film. Non-trivial would be Möbius strip or Klein bottle or something like this, okay? Now the question is, if you will discuss the effects of topology in classical magnetism, like let's say thin film community, you will have topology of the magnetization texture, so the main different micromagnetic structures, for example, the main walls, fermions, vortices, or the topology of band structure, right? So the band structure can have like topological insulators we heard today, or can be, of course, all these beautiful alter magnets, what are now a lot of discussion. So what is interesting that in this picture you are missing very important ingredient, and this important ingredient is the space in which the order parameter lives. And the space can be flat if it's a thin film, but it does not need to be flat. As for example, the Earth. Earth is not flat. Of course, it depends on the length scales which you are discussing it. But now the coupling between these three ingredients is very interesting, because you can couple band structure and texture, for example, via strain effects. Homogeneous strain, magnetostriction, inhomogeneous strain, flexomagnetic effects. So basically you can change band structure and it will have an effect on the texture. The curvilinear magnetism, this is a scene which couples the two guys on top. It couples the topology of the geometry and the topology of the texture. So this is physics, the physical, basically, essence of the curvilinear magnetism, exactly in this type of coupling. So how does it work? So in principle, let's just do experimental. So here we start with experiment. Just let's realize such kind of a tetrapod structure. Tetrapod structure, in this case, it's written by focused ion beam induced deposition. It's a group of Michael Huth in Frankfurt. They write such kind of object, which is characteristic size about 1 micrometer, and the nanowire which you use in order to create the tetrapod is about 100 nanometer. It's a soft magnetic material, cobalt iron, and if you will put this structure in X-ray microscope, you will be able to see basically where magnetization is pointing. So symmetry here is very, very high, so it's very easy to reconstruct. You will see that magnetization goes in, out in a top pair of legs and in, out in a bottom pair of legs. So it's more like a global anti-vortex type of configuration. Okay. Now the interesting part where topology comes into play here is actually the surface. The surface of this object is actually closed, and the surface is homeotopic to a sphere. So the tetrapod or n-pod in general will have a topology exactly the same as a sphere. And now the topology has a very interesting consequences. So you can apply for the magnetic vector field, it's just a vector field, on a compact manifold, which is a closed surface. You can basically characterize it with a specific topological properties like Euler characteristic, for example. Euler characteristic of a sphere is exactly +2. +2, not -2, not anything else, but +2. It means that the number of sources has to be exactly +2 in excess of number of sinks. In magnetism, we call sources vortices and sinks anti-vortices. It's two basically solitons which have different topological properties. So vortex has positive topological number and the anti-vortex has negative. So basically in this case, what this theorem tells you that on such kind of object like an n-pod, you should have excess of 2 vortices compared to number of anti-vortexes. And what I tell here is that if you will have n vortices, there has to be n-2 anti-vortexes. Very simple. Right? So total number of solitons will be 2n-2. Very simple. So everything what I just told, it's simply exactly the same as to tell that on a sphere, the ground state will be 2 vortexes. Okay? So that's exactly the same from topology point of view. So what do we have in a tetrapod? So tetrapod is homeotopic to a sphere. And if you will analyze the high resolution magnetic texture in this thing, you will see that indeed at each of the tops of the legs, you will have vortex. And in the center of the leg, you will have anti-vortex, 2 of them. So in total, you will have 2 anti-vortices and 4 vortices. So total vorticity will be +2. with the 6 solitons in total. Yeah, very simple. So now if you know this, then you can tell, all right, now I have a compact object which can contain many, many solitons. How would you create many solitons in compact manifold? Well, you have to play a trick. You have to play with topology. And the funny thing that with a sphere, unfortunately, you cannot do much because sphere has number of solitons excess plus 2. Okay? So what you have to do, you have to go to the next topological object, and this would be torus. So if you will have a torus, basically you need to have a tetrapod with a link. Okay? If you will put a linkage, you will have a loop, and the loop will be torus. Okay? So number of legs will give you a number of vortices, and the loop will tell you that how many anti-vortices you should have in a system. And in this case, what you are doing now, you are playing actually with a wireframe, and now the number of solitons is dependent by the Euler characteristic of this object. Euler characteristic of n torus is 2, and in brackets 1 minus n, where n is number of holes. Okay? So for example, for the cube, you will have 5 holes, right? You're calculating 5 inner holes, and in this case, the number of solitons will be 8. The very interesting thing is the sign. Sign is minus. So it has to be minus 8. Okay, so excess of anti-vortices. So the standard soliton in a 3-dimensional object would be not a vortex, but anti-vortex. Now, if you will have the possibility to create, like what people do experimentally, it's like a C60 molecules and buckyballs and everything. It has 60 vertices. It means that in this object, you will have, in a confined space of a magnetic microstructure, excess of 60 anti-vortices, which can interact. And this is beautiful because now you can, for example, tell, okay, have a weakly interacting gas of magnetic solitons. You can apply it to, I don't know, to some reservoir computing or something like this, if you're interested in this. Yeah? But the beautiful thing is it comes from topology, simple topology consideration of the wireframe. Instead of summary, so basically I would like to repeat this slide, and the slide is very impactful, not only because of equations, but because of the consequence. And consequence is very simple. Now you have to use the geometry as an additional mean in order to play with material science. Basically, you can adjust the properties and responses of your materials by the geometry, which is complementary, which is beautifully complementary to what you do in conventional material science when you do strain engineering, doping, I don't know, interface engineering. Yeah? What is nice here that these magnetic structures are now already kind of described in a textbook manner. So basically you have really like infinite tables of this type, where even the very young students who are not really familiar maybe with all this analytical geometry and equations and derivatives can simply find the object and tell, okay, what is the impact of curvature, for example, on the physical properties of my object. So if you will have, I don't know, a cylinder with easy axis or hard axis anisotropy, what will actually change in your system? And this is only a table, right? So it's very, very interesting. Something what I did not discuss, it's dynamics. I discussed only statics, but of course magnetization dynamics is very interesting in 3-dimensional objects. You have a lot of strain. So just imagine you have a thin film, you just bend it in a tube. You will create a strain, and the strain can be inhomogeneous. And this is exactly what is very important for 2D magnets, like chromium iodine and things like this, where you will be able to also create very interesting spin orientation transitions in such kind of curved geometries. And what is even maybe more interesting, and it comes very, very close to what we are also doing, is artificial multiferroics, because in the texture of such kind of curved object, you can have a very interesting objects emerging, which is called magnetoelectric multipoles. So it can be anapoles or toroidal moments. And this is exactly the object which couples electric polarization and magnetic order parameter in artificial structures. And this is exactly what I think is very interesting to consider as artificial multiferroic type of things based on geometrically curved objects. So if you like such kind of topic, there is a book which I had the pleasure to co-edit with Dennis Shekhar. Of course, I would be very happy if there will be any interest from your side to collaborate. So we are very, very open to collaborate. Thank you very much for your attention.
Please, questions?
My question is like from a fundamental question, like what is the difference between non-collinear Hall effect and the topological Hall effect, which is induced by the magnetic spin structure?
Yeah. Well, for anomalous Hall effect or any kind of other topological Hall effect, you need conventionally time reversal symmetry broken, right? So this is like a classical approach to Hall effect. In non-linear Hall, not collinear, but not linear Hall effect, in principle, you rely on materials with preserved time inversion, but you need non-centrosymmetric structure. So basically, there has to be non-centrosymmetry. It can be on a lattice level, but it can be also a simple geometrical symmetry break. So there is, this is the only ingredient which you need. Yeah.
Thank you for your beautiful presentation. Only one point. You know that such complicated topologies like that of Möbius band, for example, have been realized by self-organization and by direct line. But to the best of my knowledge, these methods were applied to dielectrics or to superconductors. Have such structures been fabricated for magnetic materials? And if yes, how can one control the pattern of magnetization if it is direct writing?
Well, they were on a micro scale. There is a group in Zaragoza, and they did FABIT, so this focused electron beam induced deposition of soft magnetic cobalt iron in a Möbius shape. So in principle, this is possible. The way how to control the state is given, of course, by the materials. Or is it easy axis anisotropy, or it's easy plane, which cobalt iron is easy plane. So in this case, what you would expect is actually more like a homogeneous vector field on a Möbius stripe. The only thing is where you will have a twist, like in the Möbius stripe, there will be a little bit of turning of magnetization out of surface. So that's exactly like a prediction what you would expect. Of course, if you will make it thicker and thicker, which experimentally is actually what is happening, well, it's not easy. It's basically what is happening. It is how it is. Yeah. Of course, then magnetostatics will be strong, and it will basically put magnetization more and more in plane. So observing these effects becomes very, very challenging, right? So. But what is interesting is where you will have easy access. If you will have an easy access, then it's very intuitively understandable what will happen, because if you will have an easy access and you will go across the Möbius, you must end up in the opposite orientation after you come 360 degrees, right? So you will have a pi phase in magnetic vector field after you go on the Möbius, right? And that would mean in magnetic language would be a domain wall. So this domain wall is a topologically protected domain wall because it must be there because of the geometry. It's a so-called topological patterning in magnetic structures. So this thing was never really observed, but it would be, of course, something which is really beautiful to observe.
Thank you.
Session for today, before afternoon.
Ladies and gentlemen, I'd like to make a short information. For those who don't know, we would like to stay on time with the next session. So in order to get some lunch, the nearest place to this premises is just 20 minutes outside, to the left, outside this building. When you exit the building, there is a canteen over there. So just, you can eat there really fast, and yeah, That's one of the possibilities in the premises of the, of this area, right? So enjoy your lunch and try to stay tuned to this 2 o'clock session, okay? Thank you.